Welcome. Find a comfortable position, let your breathing slow, and prepare to explore a fascinating realm where materials seem almost alive. Tonight, we journey into the world of smart materials, substances that respond, adapt, and even heal themselves. Let these ideas wash over you gently, like waves on a shore. Imagine for a moment that the buildings around us, the bridges we cross, the structures that shelter us, could sense damage and repair themselves. Imagine materials that remember their original form, that can spring back to life after being bent or broken. This isn't science fiction. This is the emerging reality of smart materials, and tonight, we'll explore how they work, why they matter, and what they promise for our future. Let's begin with a simple but profound idea. Smart materials can respond to their environment by changing shape or properties. Think about that for a moment. Most materials we encounter in daily life are passive. A steel beam simply sits there, bearing weight. A concrete slab endures footsteps and weather without reaction. But smart materials are different. They interact with the world around them. When the temperature changes, they might shift their shape. When stress is applied, they might alter their structure. When damage occurs, they might begin to heal. This responsiveness is what makes them smart. Like a plant turning toward the sun or skin forming a scab over a wound. These materials have built-in reactions to external stimuli. They sense, they respond, they adapt. In a way, they blur the line between the living and the non-living, between the organic and the engineered. Now, let's focus on one of the most remarkable properties some of these materials possess. Some materials can remember their original form after deformation. Pause and consider the implications of this. You could bend something, twist it, distort it completely, and yet somehow, under the right conditions, it would return to exactly the shape it started with. It's as if the material has a memory, an internal blueprint of what it's supposed to be. This isn't magic, of course. It's metallurgy, chemistry, and physics working in harmony. But the effect can seem almost magical. Picture a wire bent into a tangled mess, then watched as it slowly, smoothly untwists itself back into a perfect straight line. Or imagine a crumpled piece of metal that, when warmed, springs back to its original flat sheet. This memory, encoded at the molecular level, gives these materials extraordinary potential. Which brings us to a specific family of these memory-possessing materials. Shape memory alloys, often called SMAs, return to a preset shape when heated. These are typically metal alloys, combinations of elements like nickel and titanium, that exhibit this remarkable behavior. At low temperatures, you can deform them relatively easily. They'll hold that deformed shape, seemingly plastic and compliant. But apply heat, raise the temperature past a certain threshold, and something extraordinary happens. The atoms rearrange themselves into their preferred, remembered configuration. The material transforms before your eyes, returning to the shape it was trained to remember. This shape memory effect happens because of a phase transformation at the atomic level. At cooler temperatures, the alloy exists in what's called a martensitic phase, where atoms are arranged in a way that allows easy deformation. But when heated, it transforms to an austenitic phase, a more rigid, ordered structure that corresponds to the original shape. The material essentially has two personalities, two different arrangements of atoms, and heat is the trigger that switches between them. The applications are elegant and practical. Imagine medical stents that can be inserted into blood vessels in a compact form, then expand to their full size once they warm to body temperature. Or consider actuators in aerospace engineering that change shape in response to temperature changes, adjusting aircraft surfaces for optimal performance. These materials work quietly, without motors or electronics, powered only by temperature change. But shape memory alloys aren't the only smart materials revolutionizing engineering. Self-healing concrete can repair cracks automatically. Let that sink in for a moment. Concrete, one of the most common building materials on Earth, one that we associate with permanence and rigidity, can now heal its own wounds. Traditional concrete is strong in compression but weak in tension, prone to cracking over time. These cracks are more than cosmetic problems. They allow water to seep in, corroding reinforcing steel, accelerating deterioration, weakening the entire structure. For decades, we've accepted this as an inevitable fact of construction. Concrete cracks. We repair it. It cracks again. But what if the concrete could repair itself? Self-healing concrete achieves this through several clever mechanisms. One approach involves embedding tiny capsules filled with healing agents throughout the concrete. When a crack forms and breaks open these capsules, the healing agent is released directly into the crack. There, it can react with moisture or other compounds to form new material that fills and seals the crack. It's like having millions of tiny repair kits distributed throughout the structure, waiting to be activated only when and where they're needed. Another approach uses bacteria. Yes, actual living bacteria embedded in the concrete. These microorganisms remain dormant in the dry, harsh environment of concrete. But when a crack opens and water enters, the bacteria awaken. They consume nutrients that were also embedded in the concrete and produce limestone, calcium carbonate, which fills the crack. The bacteria essentially knit the concrete back together, using the same mineral that makes up much of concrete structure anyway. These innovations aren't just clever, they're necessary. These materials reduce maintenance and improve resilience. Consider the scale of our built environment. The bridges, buildings, roads, tunnels, and dams that support modern civilization. All of this infrastructure requires constant maintenance, inspection, and repair. The costs are staggering, not just financially, but in terms of time, disruption, and safety. Smart materials offer a different approach. Instead of waiting for damage to be detected and then scheduling repairs, the materials take care of minor damage themselves. A small crack in concrete seals itself before water can penetrate. A shape memory alloy component returns to its proper form after being stressed. The structure maintains itself, at least to a degree, reducing the burden on maintenance crews and extending the useful life of the infrastructure. This matters because damage in structures is unavoidable over time. No matter how well we design and build, entropy is always at work. Temperature cycles expand and contract materials. Loads stress components. Moisture corrodes and weakens. Vibrations fatigue metal. The sun's ultraviolet radiation degrades polymers. Even the best materials in ideal conditions gradually deteriorate. In many cases, the damage is subtle at first. A hairline crack here, a slight deformation there. But these small imperfections propagate. Water finds its way in. Freeze-thaw cycles widen cracks. What began as minor damage becomes structural failure. This progression is natural, predictable, and until now, largely unavoidable. We could only slow it through protective coatings, regular inspections, and timely repairs. But smart materials change this equation. They don't eliminate damage, but they can interrupt its progression. A self-healing material doesn't just sit there as cracks grow. It actively counteracts the damage, buying time, maintaining integrity, keeping the structure functional longer. This is particularly important because repairing infrastructure is expensive and dangerous. Think about what it takes to repair a crack in a bridge deck. First, the damage must be detected, which requires regular inspections, often by workers in precarious positions or using expensive equipment like drones or robots. Then the repair must be planned and scheduled. Often, lanes must be closed, disrupting traffic. Workers must access the damaged area, which might require scaffolding, lifts, or other equipment. The repair itself requires materials, skilled labor, and time. And during all of this, there's risk. Workers are exposed to traffic, heights, heavy equipment. Accidents happen. Now multiply this by thousands of bridges, millions of buildings, countless miles of roads and pipelines. The scale of infrastructure maintenance is almost incomprehensible. In many developed nations, infrastructure is aging faster than it can be repaired. Budgets are insufficient, skilled workers are scarce, and every delayed repair increases the risk of catastrophic failure. This is why smart materials aren't just a clever innovation. They're a potential solution to a looming crisis. Smart materials aim to recover function after damage. Instead of requiring human intervention for every crack and deformation, these materials handle the minor damage themselves. This doesn't eliminate the need for maintenance entirely, but it dramatically reduces it. Inspections can be less frequent. Repairs can focus on major issues rather than countless minor ones. Resources can be allocated more efficiently. The vision is of infrastructure that is more autonomous, more resilient, more forgiving of the inevitable wear and tear of service. A bridge that heals its own cracks. A building frame that returns to true after an earthquake. Water pipes that seal their own leaks. These aren't fantasies. They're engineering goals, and they're increasingly achievable. This is why shape memory alloys and self-healing concrete are studied together in civil engineering. At first glance, they might seem unrelated. One is a metal with unusual thermal properties. The other is a concrete with embedded healing mechanisms. But both serve the same ultimate purpose: creating structures that can maintain their function despite damage. Researchers and engineers explore how these materials can work together. Perhaps a building frame uses shape memory alloys in connections that can absorb seismic energy and then return to their original configuration, while the concrete components use self-healing technology to seal any cracks that form. The combination provides multiple layers of resilience. The structure bends but doesn't break, and any minor damage repairs itself. This integrated approach represents a shift in how we think about construction. We're moving away from the idea that materials should simply be as strong as possible, that structures should resist all forces. Instead, we're embracing the idea that damage is inevitable, but recovery is achievable. We're designing not just for strength, but for resilience, for the ability to maintain function through damage and repair. And what is the ultimate goal of all this research and innovation? The goal is longer-lasting, safer structures. Longer-lasting because materials that can repair themselves don't deteriorate as quickly. The gradual accumulation of minor damage, which normally weakens structures over decades, is counteracted. Components maintain their integrity longer. Service life extends from decades to perhaps a century or more. Safer because structures that can self-repair don't fail as suddenly or catastrophically. There's a built-in redundancy, a margin of safety that traditional materials don't provide. And safer too, because fewer workers need to risk their lives performing routine maintenance on aging infrastructure. Imagine a future where bridges rarely need repair, where buildings survive earthquakes with minor damage that heals within days, where the infrastructure we build today serves not just our generation, but our grandchildren's generation. This is the promise of smart materials. This is why engineers and scientists devote their careers to understanding and developing these technologies. As you rest tonight, consider the quiet revolution happening in materials science. All around us, researchers are teaching materials to sense, to remember, to heal. They're blurring the boundary between the living and non-living, creating substances that respond and adapt. The concrete and steel that form our world are becoming smarter, more capable, more alive in their own way. Let these thoughts settle gently in your mind. The idea that materials can remember, can heal, can respond. The vision of infrastructure that maintains itself, that serves us longer and more safely. It's a future being built right now, one innovation at a time, one smart material at a time. Rest well, knowing that the structures around you are becoming more resilient, that the materials of tomorrow will be wiser than those of today, and that human ingenuity continues to find new ways to build a better, longer-lasting world. Let your thoughts drift gently toward the atomic realm, where materials transform and remember. Tonight, we delve deeper into shape memory alloys, exploring the elegant science that gives these materials their remarkable abilities. Let the complexity wash over you like a gentle tide. There's no need to grasp everything at once. Simply listen, and let understanding come naturally. We've spoken of materials that remember, that return to their original form when heated. But how does this actually work? What happens inside these alloys at the level of atoms and crystals? The answer lies in one of nature's most elegant phenomena: the ability of matter to exist in different ordered states, different arrangements, each with its own properties. Shape memory alloys switch between martensite and austenite crystal phases. These names might sound technical, almost intimidating, but the concept is beautifully simple. Think of ice and water. Same molecules, same chemical composition, but arranged differently, and therefore behaving completely differently. Ice is solid, rigid, holds its shape. Water is fluid, adaptable, takes the shape of its container. The molecules haven't changed, but their arrangement has, and that changes everything. Martensite and austenite are like that. They're the same atoms, the same elements, the same alloy. But in martensite, the atoms arrange themselves in one particular crystalline structure. In austenite, they arrange themselves in another. Same material, different arrangements, profoundly different properties. And remarkably, the material can switch between these arrangements in response to temperature. Let's explore martensite first, the low-temperature phase. Martensite is soft and easily deformed. When a shape memory alloy is cool, below its transformation temperature, it exists in this martensitic state. The crystal structure is what scientists call twinned. Imagine layers of atoms arranged in one direction, adjacent layers arranged in a slightly different direction, back and forth, creating a zigzag pattern at the microscopic level. This twin structure is clever. It allows the material to accommodate stress easily. When you bend or stretch the alloy in its martensitic state, you're not actually moving individual atoms very far. Instead, you're causing some of those twin boundaries to shift. Layers that were angled one way reorganize to angle another way. The overall crystal structure remains martensitic, but its orientation changes. This is why the material seems soft and pliable when cool. It's not that the atomic bonds are weak. It's that the structure can reorganize without breaking those bonds. Think of it like a deck of cards. If you push sideways on a neatly stacked deck, the cards slide past each other easily. You've deformed the deck dramatically, but you haven't bent or broken any individual card. The martensite phase works similarly. Deformation happens through reorganization rather than through elastic stretching of bonds. So when you bend a cool shape memory alloy wire, it stays bent. The martensitic structure has reorganized to accommodate that new shape. To the casual observer, it looks like the material has been permanently deformed, like any ordinary metal that's been bent beyond its elastic limit. But this deformation is different. It's temporary. The structure has changed, but not irreversibly. The memory remains waiting for heat. Because while martensite is soft and deformable, there's another phase, a high-temperature phase with very different properties. Austenite is strong and returns to the original shape. When you heat the alloy past a critical temperature, something remarkable happens. The atoms don't like being in the martensitic arrangement anymore. That crystal structure, which was stable and preferred when cool, becomes unstable when warm. The atoms begin to rearrange. They shift positions, reorganize their bonding, transform the crystal lattice from the twinned martensitic structure to a different structure entirely, austenite. This austenitic structure is typically cubic, more symmetrical, more ordered. And critically, it's the structure the alloy was in when it was trained, when it was taught its remembered shape. In the austenite phase, the material is much stiffer, much stronger. Those twinned boundaries that could slide easily in martensite don't exist in austenite. The cubic crystal structure is more rigid. Deformation now would require actually stretching atomic bonds or breaking the crystal structure, which takes much more force. So the austenite phase resists deformation far more than martensite does. But here's the magic. When the transformation from martensite to austenite occurs, the material doesn't just become stiffer. It returns to its original geometry. All those twin boundaries that shifted during deformation, all that reorganization of the martensitic structure gets erased. The atoms find their way back to the positions they occupied in the original austenite configuration. The bent wire straightens. The crumpled sheet flattens. The deformed component returns to true. This happens because heating triggers the phase transformation. Temperature is the key that unlocks the memory. Below the transformation temperature, martensite is stable and preferred. Above it, austenite is stable and preferred. Cross that threshold and the material transforms, driven by thermodynamics, by the fundamental laws that govern how atoms arrange themselves at different energy states. The transformation isn't instantaneous across the entire sample. It nucleates, beginning at certain points and spreading like crystal growth. You can sometimes see or feel this if you heat a shape memory alloy slowly. The material recovers in waves, in pulses, as regions transform from martensite to austenite. It's a progression, a cascade of atomic rearrangement sweeping through the material. And just as heating causes the transformation from martensite to austenite, cooling reverses the transformation. Let the alloy cool back down, and austenite becomes unstable again. Martensite becomes preferred. The atoms reorganize once more, transforming back to the twin structure. The material becomes soft again, ready to be deformed again, ready for the cycle to repeat. This reversibility is crucial. The shape memory alloy doesn't exhaust itself with one transformation. It can cycle many times, thousands or even millions of times depending on the specific alloy and conditions. Heat, cool, and each time the material transforms, remembers, returns. It's a fatigue-resistant form of actuation, a way to convert thermal energy directly into mechanical motion. Now, we've been focusing on what's called the shape memory effect, but these alloys have another remarkable property. The shape memory effect restores geometry after deformation and heating. You deform when cool, heat it up, and it returns. But there's a related phenomenon that works differently. Supraelasticity allows large reversible strains. Supraelasticity, sometimes called pseudoelasticity, occurs when the alloy is held at a temperature just above its normal transformation temperature. In this regime, the material exists in austenite at rest. But when you apply stress, when you pull or bend it, that mechanical stress is enough to trigger a local transformation to martensite. The stress essentially pushes the transformation temperature down for the material under load. So as you stretch the wire, regions transform from austenite to martensite under your pull. The martensite accommodates the deformation easily, just as we discussed before. You can stretch the wire to enormous strains, far beyond what ordinary metals could withstand elastically. But here's the key. As soon as you release the stress, those regions transform back to austenite immediately. The mechanical driving force is gone, temperature is above the normal transformation point, so austenite is preferred again. The wire snaps back to its original length. This isn't normal elasticity, where atomic bonds stretch and then relax. This is phase transformation and reverse transformation, happening in real time as you load and unload the material. It feels elastic, it looks elastic, but the mechanism is entirely different. And it allows for deformations of 8, 10, even 15% strain that recover completely. Ordinary metals might offer 1% elastic strain at most. Supraelastic shape memory alloys can give you 10 times that or more. This property makes them invaluable for applications like eyeglass frames that can bend dramatically without breaking, or orthodontic wires that maintain constant force as teeth move, or medical guide wires that can navigate tortuous blood vessels and then straighten perfectly when the stress is removed. But we must be careful with temperature control, because these transformations don't happen at a single precise temperature. Thermal hysteresis separates heating and cooling temperatures. Hysteresis means there's a lag, a difference between the forward and reverse process. The temperature at which martensite transforms to austenite during heating is different from the temperature at which austenite transforms back to martensite during cooling. Imagine you're heating a shape memory alloy. It might begin transforming to austenite at, say, 60 degrees Celsius and complete the transformation at 80 degrees. But when you cool it back down, it might not begin transforming to martensite until 50 degrees and complete at 30 degrees. There's a gap, a hysteresis loop. The transformation temperatures are different depending on whether you're heating or cooling. This happens because phase transformations have energy barriers. It takes energy to reorganize all those atoms from one crystal structure to another. On heating, you need to reach a high enough temperature that the austenite phase is not just slightly preferred, but strongly preferred enough to overcome the energy barrier. On cooling, similarly, you need to cool below the equilibrium point enough to drive the reverse transformation. This hysteresis is actually useful in many applications. It means the material has thermal stability in both phases. If the transformation happened at a single sharp temperature in both directions, the material would be constantly flickering between states with tiny temperature fluctuations. The hysteresis provides a buffer zone, a range where the material stays in one phase or the other, stable and predictable. But engineers need to account for it. They need to know not just that the material transforms, but at what specific temperatures it transforms during heating and during cooling. These temperatures define the operating window for any device using shape memory alloys. And importantly, transformation temperatures depend on alloy composition. This is one of the most powerful aspects of shape memory alloys. We can tune them. By adjusting the ratio of elements, by adding small amounts of other metals, we can shift the transformation temperatures up or down, widen or narrow the hysteresis, even modify the strength of the phases. The most common shape memory alloy is Nitinol, an alloy of nickel and titanium in roughly equal proportions. Nitinol's transformation temperatures can be adjusted across a huge range, from well below 0 Celsius to over 100 degrees, simply by changing the exact nickel to titanium ratio by a few percent. Too much nickel, and the transformation temperatures rise. Too much titanium, and they fall. Other alloying elements add further control. A tiny addition of copper can narrow the hysteresis, making the transformation sharper. Adding iron or chromium can lower transformation temperatures. Adding hafnium can raise the operating temperature for high-temperature applications. The possibilities are vast, and metallurgists continue to develop new compositions for specific needs. This tunability means shape memory alloys can be designed for their application. Need an alloy that activates at body temperature for a medical implant? We can make that. Need one that activates at 150 degrees for an automotive application? We can make that too. Need a wide hysteresis for stability or a narrow hysteresis for responsiveness? Both are possible. But how does the alloy learn its remembered shape in the first place? This is where the final piece of the puzzle comes in. Heat treatment trains the remembered shape. A shape memory alloy doesn't naturally remember any particular configuration. When first produced, it's just a piece of metal. The memory must be taught. The training process is elegant. You shape the alloy into the form you want it to remember. Perhaps you wrap a wire around a mandrel to create a coil. Perhaps you press a sheet into a specific curve. Perhaps you machine a component to precise dimensions. Whatever the desired shape, you form the alloy into that shape while it's in its high-temperature austenite phase. Then you heat it significantly, typically to 500 degrees Celsius or even higher, well above the transformation temperatures. You hold it at that temperature for a period of time, perhaps minutes, perhaps hours, depending on the alloy and the size of the component. During this heat treatment, something remarkable happens at the atomic level. The crystal structure of the austenite phase becomes associated with this particular macroscopic shape. The orientations of crystal grains, the distribution of any defects or stresses, the overall configuration of the material all become locked in at the high temperature. When the material cools and transforms to martensite, it can be deformed. But that high-temperature austenite configuration remains encoded somehow in the material's structure. The exact mechanism is complex, involving preferential orientations of martensitic variants, internal stresses, and the memory of the austenite grain structure. But the result is clear. After training, whenever the material is heated back to austenite, it returns to that trained shape. The atoms find their way back to the configuration that was set during the heat treatment. Some alloys can even be trained multiple times for different shapes at different temperatures, creating two-way shape memory or multiple memory effects. These advanced behaviors require sophisticated training procedures, carefully controlled thermal cycling, and sometimes mechanical loading during training. But they demonstrate the remarkable control we have over these materials. As you rest tonight, imagine atoms rearranging themselves in orchestrated patterns. Envision crystal structures transforming, twins shifting, order emerging from disorder, and then dissolving back into a different kind of order. See in your mind a wire bending, crumpling, seemingly broken, then slowly, smoothly returning to perfection as invisible atomic forces guide it back. This is the science of shape memory alloys. Not magic, but something perhaps more wondrous. The predictable, repeatable behavior of matter following physical laws. We've learned to speak the language of atoms, to understand their preferences, to guide their arrangements. And in doing so, we've created materials that seem almost alive, that respond and remember and recover. Let these ideas settle gently as you drift towards sleep. The elegance of phase transformations, the poetry of crystal structures rearranging, the simple beauty of materials that remember their purpose and return to it, time and time again, faithful to the shape they were taught, guided by nothing more than temperature and the fundamental laws of thermodynamics. Rest well, knowing that matter itself is more flexible, more capable, more surprising than we often imagine. And know that human understanding of these atomic behaviors continues to deepen, opening new possibilities for materials that serve us better, that last longer, that respond more intelligently to the world around them. Sleep peacefully, and let the transformation from waking to rest be as smooth and natural as martensite becoming austenite, as gentle and inevitable as a shape memory alloy returning home. Welcome once more to this quiet exploration of intelligent materials. Let your mind settle into the realm where theory meets practice, where the elegant science of shape memory alloys encounters the practical challenges of engineering. Tonight, we examine how these materials are actually used, what limits they face, and how engineers work within those boundaries to create useful devices. Breathe slowly, and let these practical considerations unfold like a gentle story. We've explored the science of how shape memory alloys transform and remember. Now we turn to a crucial question. What can they actually do? How do they work in the real world? The answer begins with force. Shape memory alloys generate force through phase change contraction. This is their superpower, their primary value as engineering materials. When a shape memory alloy transforms from martensite to austenite, it doesn't just change its crystal structure, it changes its dimensions. The austenite phase is typically slightly more compact than the deformed martensite phase. So as the transformation sweeps through the material, it contracts. If the material is constrained, if something prevents it from contracting freely, it generates force against that constraint. And this isn't gentle force. Shape memory alloys can generate stresses of hundreds of megapascals during transformation. That's comparable to high-strength steel. A thin wire, perhaps a millimeter in diameter, can pull with dozens of newtons of force. A larger component can generate hundreds or thousands of newtons. This force comes from the collective action of countless atoms rearranging themselves, and it's surprisingly powerful. This makes shape memory alloys natural actuators. An actuator is simply a device that creates motion or force, something that does mechanical work. We're surrounded by actuators in daily life. Electric motors that spin, pneumatic cylinders that push, hydraulic rams that lift. Shape memory alloys join this family as thermal actuators, converting heat energy directly into mechanical work. Imagine a simple setup. A shape memory alloy wire stretched between 2 points, pulling against a spring. When cool, the wire is in martensite, and the spring holds it extended. Heat the wire, and it transforms to austenite, contracting with considerable force. The wire pulls, overcomes the spring, and moves whatever is attached to it. Cool it again, and the spring pulls the wire back to its extended length. The wire is ready for another cycle. This is the basic principle behind thousands of SMA actuator designs. The details vary endlessly. Different configurations, different loads, different heating methods, but the core concept remains. Heat triggers transformation, transformation generates force and contraction, cooling allows reset. The amount of contraction available is significant. Recoverable strain can reach 5 to 8%. Strain is the engineering term for deformation relative to original size. 5% strain means a 100 mm wire can contract by 5 mm. 8% strain means 8 mm of contraction. This might not sound dramatic, but in the world of actuators, it's remarkable. Most materials offer tiny elastic strains, fractions of a percent. Even piezoelectric materials, which convert electrical energy to motion, typically provide strains of only 0.1% or less. Shape memory alloys offer 50 to 100 times more displacement in a single transformation. This large strain is useful for many applications. It means a short wire can provide significant motion. It means actuators can be compact, yet deliver useful displacements. In robotics, in aerospace, in medical devices, where space is precious and every gram matters, this combination of high force and large strain makes shape memory alloys attractive. But there's more. The transformation we've described so far is one way. The alloy contracts when heated but needs an external force, like a spring or bias weight, to stretch it back out when cooled. This is called one-way shape memory. But there's another mode, more complex but also more versatile. Two-way shape memory can be induced by training. Two-way shape memory means the alloy has two remembered shapes, one in the austenite phase and a different one in the martensite phase. Heat it, and it takes shape A. Cool it, and it takes shape B. Heat it again back to shape A. Cool it again back to shape B. No external force needed. The material moves back and forth on its own, driven only by temperature changes. This doesn't come naturally. It must be taught through a process called thermomechanical training. The alloy is cycled repeatedly through its transformation temperatures while under stress or constraint. Over many cycles, sometimes hundreds or thousands, the material develops internal stresses, preferred orientations of martensite variants, and microstructural features that favor certain deformations in the martensite phase. After sufficient training, the alloy remembers both configurations. In austenite, it adopts the shape set during heat treatment. In martensite, it adopts a different shape, learned through the training cycles. This two-way memory is less robust than one-way memory. The martensite shape is held by internal stresses rather than by the austenite crystal structure, so it generates less force and can degrade over time. But for applications where no external bias is possible or desired, two-way memory opens new possibilities. Imagine a solar tracker that adjusts itself throughout the day using a two-way memory alloy, curling when cool in the morning and straightening when heated by afternoon sun, then curling again as evening approaches. Or a ventilation louver that opens when a room warms and closes when it cools, with no power source except ambient temperature change. These passive, heat-driven devices leverage two-way memory beautifully. But in many applications, we don't want to wait for ambient temperature changes. We want precise control, rapid actuation, predictable timing. This is where active heating comes in. Electrical current can actuate shape memory alloys via Joule heating. Joule heating is the phenomenon where electrical resistance generates heat. When current flows through a conductor, collisions between moving electrons and the atomic lattice convert electrical energy to thermal energy. The wire warms up. Shape memory alloys are moderate electrical conductors. Pass a current through an SMA wire, and it heats up, often quite rapidly. The current needed depends on the wire diameter and the desired transformation speed, but it's typically quite manageable. A thin wire might need just a few hundred milliamps. A thicker wire might need several amps. Standard electronics can easily provide and control these currents. This electrical actuation is elegant. The wire itself is the heating element. No separate heater is needed. The response can be fast, limited primarily by how quickly heat can be generated uniformly throughout the wire. Small diameter wires can transform in a fraction of a second. Larger components might take seconds or tens of seconds, depending on their thermal mass. Cooling is more challenging. It happens passively, through heat loss to the surroundings. The rate depends on the surface area, the thermal conductivity of the environment, any air flow or liquid cooling present. Small wires cool faster than thick ones. Wires in air cool slower than wires in water or oil. Engineers must design for adequate cooling, sometimes adding fins or heat sinks, sometimes using forced air or liquid flow. This ability to actuate with simple electrical heating makes shape memory alloys easy to integrate into electronic control systems. A microcontroller can switch current on and off, pulse width modulate it for temperature control, even measure the wire's resistance to estimate its temperature and transformation state. The actuator becomes part of an intelligent system, responding to sensors and control algorithms. And where traditional actuators struggle with space constraints, shape memory alloy actuators replace motors in tight spaces. Think about a small electric motor. It needs a rotor, a stator, bearings, housing. It has minimum size constraints based on magnetic field requirements and mechanical clearances. Below a certain size, motors become inefficient, expensive, difficult to manufacture. Shape memory alloys bypass all this. A wire actuator is just wire, perhaps with crimped terminals or simple end fittings. It can be routed through narrow channels, wrapped around obstacles, integrated into structures. There are no gears to mesh, no bearings to align, no magnetic fields to generate. The simplicity is profound. This makes SMA actuators ideal for microrobots, miniature surgical tools, tiny adaptive mechanisms in compact electronics. Anywhere size and complexity are critical concerns, shape memory alloys offer advantages. They've been used in medical catheters no thicker than a pencil lead, in miniature aircraft that fit in your hand, in cell phone camera autofocus mechanisms measured in millimeters. But electrical actuation brings design challenges. Heating and cooling rates must be controlled. Heat too quickly, and the transformation might be uneven, or the wire might overshoot its target temperature, wasting energy and potentially degrading the material. Heat too slowly, and the actuator responds sluggishly, defeating the purpose of its use. Similarly, cooling must be managed. If the application requires rapid cycling, the cooling rate limits overall speed. Engineers must ensure adequate heat removal. They might use heat sinks, thermal pathways to cool masses, forced convection with fans or pumps. They must calculate thermal time constants, ensure the wire returns to a low enough temperature to fully transform back to martensite before the next actuation cycle begins. Temperature control often involves feedback. Sensors monitor the wire temperature or measure its electrical resistance, which changes with temperature and phase. Control algorithms adjust the current accordingly, heating to precisely the right temperature, then switching off to allow cooling. This closed-loop control maximizes performance and prevents overheating damage, because damage and degradation are real concerns. Functional fatigue reduces performance over cycles. Unlike ordinary mechanical fatigue, which is about crack initiation and propagation, functional fatigue is about gradual changes in the transformation behavior itself. The transformation temperatures might drift. The amount of recoverable strain might decrease. The force generated might diminish. The hysteresis might widen. This happens because repeated transformation cycles gradually modify the material's microstructure. Dislocations accumulate, tiny defects that interrupt the perfect crystal lattice. Residual stresses build up. The interfaces between austenite and martensite, which move back and forth with each cycle, can leave behind damage in their wake. Small precipitates or compositional variations can form, altering local transformation behavior. The rate of functional fatigue depends on many factors. The amount of strain imposed each cycle is critical. Larger strains accelerate fatigue. The stress level matters too. High stresses, approaching the material's limits, cause faster degradation. The quality of the alloy is important. Impurities, inclusions, and poor processing lead to early fatigue. Well-designed, high-quality shape memory alloy devices can cycle millions of times with minimal degradation. Medical stents, which expand once and then remain expanded, face minimal fatigue. Eyeglass frames, which experience small deformations infrequently, last for years. But actuators that cycle frequently under high strain and stress need careful engineering to achieve acceptable lifetimes. This brings us to a crucial principle: strain limits must be respected. While shape memory alloys can recover large strains during transformation, they're not invincible. Exceed certain strain limits, and the deformation becomes truly plastic, permanent. The material might still transform, but it won't fully recover. Some residual deformation remains after each cycle, accumulating until the actuator no longer functions properly. Different limits apply in different conditions. In the martensite phase, the alloy can be deformed to perhaps 8 or 10% strain and still fully recover upon heating. But push beyond that, and you begin to create permanent deformation. In the austenite phase, the material is stiffer, less tolerant of deformation. Strains of only 2 or 3% might cause permanent damage. Similarly, in supraelastic applications, there are limits. The stress-induced martensite can accommodate large strains, but exceed the yield stress of martensite itself, and you'll get permanent deformation. Engineers must carefully characterize their specific alloy, understanding its limits in all phases and conditions, then design to stay within those boundaries. This often means combining materials intelligently. Shape memory alloys are often combined with conventional metals. A hybrid structure might use SMA wires for actuation, but rely on aluminum or steel for primary load bearing. The shape memory components do what they do best: transform and generate motion, while conventional materials handle steady loads efficiently and economically. These composites take many forms. SMA wires embedded in polymer matrices, providing adaptive stiffness or shape change. Steel beams with SMA tendons that can adjust tension or camber. Aluminum frames with SMA actuators driving joints or mechanisms. The goal is to use each material where it offers the greatest advantage. This hybrid approach also helps manage cost. Shape memory alloys, particularly high-quality nitinol, are expensive compared to conventional metals. They require careful processing, precise composition control, specialized heat treatments. Using them selectively, only where their unique properties are truly needed, makes designs more economically viable. It also addresses another reality. Shape memory alloys aren't ideal for every mechanical requirement. They're not the stiffest materials, not the strongest in a simple tensile test, not the most fatigue-resistant under conventional cyclic loading. They have specific strengths: shape memory, supraelasticity, high work density. But they also have weaknesses. Good engineering recognizes both. This balance of considerations defines the engineering reality of shape memory alloys. Designers balance force, speed, and durability. These three attributes compete. Want more force? Use thicker wires or higher stress levels, but cooling becomes slower and fatigue life may decrease. Want faster actuation? Use thinner wires with rapid electrical heating, but force output drops and careful thermal management becomes critical. Want longer life? Reduce strain levels and stress, but force and displacement suffer. There's no single optimal design, only optimal designs for specific applications with specific priorities. A medical device might prioritize reliability above all else, accepting lower force and slower speed to ensure many years of dependable operation. A robotic gripper might prioritize speed and responsiveness, accepting more frequent maintenance or replacement. An aerospace mechanism might prioritize weight savings and compact size, carefully managing fatigue through limited duty cycles. Engineers work within these constraints, making trade-offs, testing prototypes, iterating designs. They use finite element models to predict stress distributions. They run thermal simulations to optimize heating and cooling. They conduct life cycle tests to validate fatigue performance. They experiment with different alloy compositions, heat treatments, and mechanical configurations. The result is a rich landscape of shape memory alloy applications, each carefully tailored to its requirements. Some succeed spectacularly. Others fail, teaching lessons about overlooked limits or underestimated challenges. This is the reality of engineering, not the idealized behavior of perfect materials in theoretical conditions, but the messy, complex, fascinating challenge of making things work reliably in the real world. As you rest tonight, appreciate the complexity behind seemingly simple devices. That stent holding open an artery? Designed with exquisite care to balance expansion force, flexibility, fatigue life, and biocompatibility. Those eyeglasses that bend but never break? Engineered to stay within precise strain limits while tolerating the unpredictable stresses of daily wear. That tiny actuator adjusting a camera lens? Optimized for speed, precision, and millions of cycles in a space smaller than your fingertip. Behind each application stands a team of engineers who understand both the promise and the limits of shape memory alloys. They know how to harness the phase transformation for useful work. They know where the boundaries lie. They know how to design within those boundaries, creating devices that work reliably, cycle after cycle, year after year. Let these thoughts of careful engineering, thoughtful trade-offs, and balanced design ease you towards sleep. The world of technology isn't just about breakthrough materials and elegant science. It's also about patient engineering, rigorous testing, and wise compromise. It's about understanding limits as well as possibilities, respecting constraints as well as pursuing innovation. Rest well, knowing that the shape memory alloy devices around you, invisible though they may be, represent countless hours of careful design, testing, and refinement. Sleep peacefully, and let your mind settle like an alloy cooling into its stable phase, finding its natural configuration, ready to transform again when called upon. But for now, simply at rest. Welcome back to this peaceful exploration of intelligent materials. Tonight we turn our attention to the materials themselves, the specific alloys that bring shape memory to life. Let yourself sink into comfort as we explore the periodic table's offerings, the combinations of elements that create these remarkable behaviors. There's a quiet poetry in the way different metals combine, each bringing its own character to the alloy. Listen gently, and let the chemistry unfold. In our journey so far, we've spoken generally about shape memory alloys, about their transformations and applications. But shape memory isn't the property of a single material. It's a behavior that emerges from many different alloy systems, each with its own personality, its own strengths and weaknesses, its own ideal applications. Tonight, we'll meet this family of materials one by one. The story begins with nickel and titanium. Nickel-titanium, known as nitinol, is the most common shape memory alloy. When most people think of shape memory materials, when engineers reach for an SMA solution, nitinol is usually what they're considering. It has become nearly synonymous with shape memory itself, and for good reason. Nitinol represents an exceptional combination of properties that make it useful across an enormous range of applications. The name itself has a story. Nitinol stands for Nickel Titanium Naval Ordnance Laboratory. NITI was developed in the 1960s by researchers at the Naval Ordnance Laboratory in White Oak, Maryland. William Bueller, a metallurgist, and Frederick Wong, an engineer, discovered the shape memory effect in this alloy somewhat serendipitously while investigating materials for missile nose cones. The story goes that Bueller had created a strip of nickel-titanium alloy and was demonstrating its properties at a laboratory management meeting. The strip had been folded and stressed repeatedly to show its unusual resilience. Someone held a lighter to the crumpled strip, and to everyone's astonishment, it suddenly sprang back to its original flat shape. The shape memory effect revealed itself in that moment, unexpected and dramatic. That was 1963. In the decades since, nitinol has been refined, characterized, and deployed in thousands of applications. Medical devices, eyeglass frames, actuators, thermal sensors, orthodontic arch wires, antennas, couplings, connectors. The list goes on and on. Nitinol has become indispensable in modern engineering. What makes nitinol so successful? Several factors combine. First, its transformation temperatures can be tuned across a wide range, simply by adjusting the nickel to titanium ratio. with roughly equal parts nickel and titanium, close to 50 atomic percent each. You can create alloys that transform anywhere from well below 0 Celsius to well above 100 degrees. This tunability means nitinol can be optimized for body temperature medical devices, for ambient temperature actuators, for automotive underhood applications, and much more. Second, nitinol exhibits excellent supraelasticity. That large, recoverable strain we discussed earlier, 8% or more, is readily achieved in well-processed nitinol. This makes it ideal for devices that need to flex repeatedly without permanent deformation: stents, guide wires, orthodontic appliances. Third, nitinol is biocompatible. Titanium is well known for its compatibility with human tissue, used extensively in implants. The nickel in nitinol is bound tightly in the crystal structure, not free to leach out significantly. With proper surface treatments and passivation, nitinol can be used safely inside the human body. This has opened the entire field of minimally invasive medicine, where nitinol devices navigate through blood vessels and other pathways. Fourth, nitinol is relatively corrosion resistant, thanks again to the titanium content. In most environments, it forms a stable oxide layer that protects the underlying metal. This durability makes it suitable for long-term applications, devices that must function reliably for years or decades. But nitinol has drawbacks too. It's expensive. Both nickel and titanium are costly elements, and processing nitinol requires careful control. The alloy is sensitive to composition. A difference of just 1% in nickel content can shift transformation temperatures by dozens of degrees. Manufacturing must be precise. The alloy is also difficult to machine and join. Traditional welding can degrade its properties. Laser welding works better, but requires expertise. Machining nitinol wears tools quickly and demands careful techniques. These challenges led researchers to explore alternatives. Copper-based shape memory alloys offer lower-cost alternatives. Copper is abundant and inexpensive compared to titanium. Alloys based on copper combined with other elements can exhibit shape memory, and they can be produced at a fraction of nitinol's cost. Two copper-based systems have received the most attention. CuZnL and CuLni suit non-critical uses. Copper-zinc aluminum alloys were among the first shape memory alloys discovered, actually predating the discovery of nitinol's shape memory by several years. Copper-aluminum-nickel alloys followed shortly after. Both systems can be formulated to show strong shape memory effects. These copper alloys have advantages. They're inexpensive to produce. They can be cast and worked using conventional metallurgical techniques. Their transformation temperatures can be adjusted through composition changes. For applications where cost is a primary driver and performance requirements are modest, copper-based SMAs are attractive. But they also have significant limitations. Their supraelasticity is poor compared to nitinol. The recoverable strain is smaller, typically 3 to 4% rather than 8%. Their fatigue resistance is much lower. Where nitinol might cycle millions of times, copper-based SMAs might manage thousands to tens of thousands of cycles before significant degradation. They're also more brittle, more prone to cracking, more sensitive to composition variations and processing defects. Perhaps most limiting, copper-based SMAs age and degrade at room temperature. Their transformation temperatures can drift over time, even when the material is just sitting and used. The microstructure gradually evolves, sometimes becoming more ordered, sometimes precipitating secondary phases. This instability makes copper-based SMAs unsuitable for any application requiring long-term reliability or precise, consistent performance. So where are they used? Training devices, demonstrators, toys, simple actuators in non-critical applications. Anywhere the low cost justifies accepting the performance limitations. They serve an important role, making shape memory accessible where nitinol would be prohibitively expensive. But for demanding applications, medical devices, aerospace systems, anything where lives or significant value depend on reliable performance, nitinol remains the standard. Yet there's another frontier, another set of applications where even Nitinol struggles. Iron-based shape memory alloys are developed for construction. The civil engineering applications we've discussed, adaptive structures, seismic damping, self-centering connections, require large components, often tens of kilograms or more of shape memory material. At Nitinol prices, this becomes economically impossible. Iron is cheap. It's the basis of steel, the most widely used structural metal. If iron-based alloys could be made to exhibit useful shape memory, the economics of large-scale structural applications would transform. This realization drove decades of research into iron-based shape memory alloys. The challenge was finding iron alloy systems with transformation characteristics suitable for practical use. Pure iron doesn't show useful shape memory, but certain iron alloys, particularly those containing manganese, silicon, chromium, and nickel in specific combinations, can be induced to show shape memory behavior. Iron-manganese-silicon alloys were among the first successes. With the right composition and thermomechanical processing, these alloys show a martensitic transformation and associated shape memory. The recoverable strain is modest, perhaps 2 to 4%, significantly less than Nitinol. But for structural applications, where forces are large and displacements can be modest, this may be sufficient. More importantly, FASMAs resist corrosion and fatigue when properly designed. Iron alloys can be formulated to withstand outdoor exposure, aggressive environments, the kinds of conditions that structural materials must endure. They can be welded, machined, fabricated using familiar steelworking techniques. They integrate easily into existing construction practices. The development continues. Researchers work to improve the recoverable strain, to increase the stability of the shape memory effect, to reduce the sensitivity to thermal cycling and aging. Iron-based SMAs haven't yet achieved widespread commercial use in structures, but they're getting closer. Demonstration projects have shown their potential. Self-centering beam column connections that can survive earthquakes, pre-stressing elements that adjust to temperature changes, coupling devices that can be activated on demand. The economics are compelling. Even if iron-based SMAs cost 10 times more than ordinary structural steel, they're still far cheaper than Nitinol. For large components, this cost difference is decisive. If the performance can be made reliable enough, iron-based SMAs will likely find their place in the next generation of adaptive structures. But some applications require the opposite extreme. Not low cost for large structures, but exceptional performance in extreme conditions. High-temperature shape memory alloys operate above 200 degrees Celsius. Nitinol's transformation temperatures, even at their upper range, rarely exceed 120 degrees. Above that, the alloy loses its shape memory behavior. Its microstructure becomes unstable. It degrades rapidly. Yet there are applications that need shape memory at higher temperatures. Jet engine components experience temperatures of 500 degrees or more. Spacecraft structures can see extreme temperature swings. Industrial processes often operate at several hundred degrees. For these environments, new alloy systems are needed. This is where exotic alloys enter the picture. TPD and T-point systems enable extreme use. Titanium palladium and titanium platinum alloys, with carefully controlled compositions, can exhibit shape memory at temperatures of 400, 500, even 600 degrees Celsius or higher. The palladium and platinum stabilize the high-temperature austenite phase, raise the transformation temperatures, and improve oxidation resistance. These alloys represent remarkable materials science achievements. They maintain the fundamental shape memory mechanism, martensitic transformation, phase-dependent properties, thermally driven actuation, but at temperatures where most shape memory alloys would melt or degrade. They enable applications that simply weren't possible with conventional SMAs. But they come at a cost. Palladium is expensive. Platinum is even more so. These alloys can cost hundreds or even thousands of dollars per kilogram. Processing is challenging, requiring high-temperature facilities and careful atmosphere control. The materials are used only where absolutely necessary, where no alternative exists, where the application justifies the extreme expense. Jet engine variable geometry actuators, spacecraft deployment mechanisms, high-temperature sensors and switches. These are the domains of high-temperature SMAs. Small components, precisely engineered, operating in conditions that would destroy any ordinary shape memory alloy. They're exotic, specialized, the cutting edge of shape memory technology. Across all these alloy systems, from copper to iron to titanium to platinum, a fundamental principle applies. Alloy composition tunes activation temperature. We've mentioned this for nitinol, but it's true for all shape memory alloys. The transformation temperatures, where martensite becomes austenite and vice versa, depend critically on the exact proportions of elements in the alloy. This composition sensitivity is both a tool and a challenge. It's a tool because it allows us to design alloys for specific temperature ranges. Need activation at body temperature for a medical device? We can dial in that composition. Need activation at 50 degrees for an automotive application? Different composition. Need activation at 400 degrees for aerospace? Yet another composition, possibly a different alloy system entirely. But it's also a challenge because it demands tight composition control during manufacturing. Small variations in composition, even fractions of a percent, can shift transformation temperatures significantly. This requires careful melting practices, homogeneous mixing, precise analytical characterization. It's one reason why high-quality nitinol is expensive. The composition must be held to very tight tolerances. Other factors also influence transformation temperatures. Thermomechanical processing, how the alloy is worked, rolled, drawn, heat-treated, can shift temperatures. Aging treatments can modify the microstructure and change transformation behavior. Even the stress state affects transformation temperatures. Applied stress can raise or lower them depending on the crystallographic orientation. All of this means that developing a shape memory alloy for a specific application is as much art as science. Metallurgists must consider the intended operating temperature range, the required mechanical properties, the expected service environment, the allowable cost, the manufacturing constraints. They select an alloy system, then fine-tune the composition, develop the processing route, test and iterate until the material performs as needed. And that performance is always a compromise. Each SMA family trades cost, range, and performance. Want the lowest cost? Copper-based alloys, but accept limited performance and stability. Want the best all-around performance? Nitinol, but accept higher cost and processing challenges. Want massive components for structures? Iron-based alloys, with modest shape memory properties, but excellent economics at scale. Want extreme temperature capability? Titanium, palladium, or platinum, with exceptional performance, but extreme cost. There is no single best shape memory alloy. There are only alloys best suited to particular applications, particular requirements, particular constraints. The engineer's task is to understand these trade-offs, to match material to application, to accept the limitations that come with the chosen material and design accordingly. As you drift towards sleep tonight, imagine the periodic table as a palette, elements as colors waiting to be mixed. Nickel and titanium combine to make silver-gray nitinol, reliable and versatile. Copper, zinc, and aluminum blend into golden-bronze alloys, inexpensive but temperamental. Iron, manganese, and silicon create structural alloys, strong but still emerging. Titanium, palladium, and platinum forge exotic alloys for extreme frontiers, costly but capable. Each combination tells a story of atoms finding new arrangements, of properties emerging from composition, of materials scientists exploring the vast space of possible alloys. Most combinations are unremarkable, but some, through fortunate atomic sizes, electronic structures, and crystal preferences, exhibit this remarkable shape memory behavior. We've discovered dozens of these combinations. We've characterized them, refined them, put them to use. And we continue searching, exploring new compositions, new processing methods, new ways to coax shape memory behavior from Earth's elements. The family of shape memory alloys grows slowly but steadily, each new member adding to our toolkit, expanding what's possible. Rest well tonight, knowing that materials science continues its patient work, mixing elements, testing combinations, discovering new behaviors. Sleep peacefully, and let your mind settle like atoms finding their preferred arrangement, stable and content. until heat or circumstance calls for transformation once again. Welcome back to this gentle journey through the world of intelligent materials. Tonight we step away from theory and chemistry to witness shape-memory alloys at work in the real world. From inside the human body to the surface of Mars, from commercial aircraft to orbiting satellites, these materials quietly serve humanity in ways most people never see. Let these stories of application wash over you, each one a testament to human ingenuity and the remarkable properties of matter itself. We begin where the impact is most personal, most intimate. Nickel titanium is used in medical stents and guide wires. Inside human bodies right now, at this very moment, millions of Nitinol devices are working silently. Stents hold open arteries, restoring blood flow to hearts and brains and limbs. Guide wires navigate through tortuous blood vessels, leading catheters and other tools to treatment sites deep within the body. Consider the stent first. A stent is a tiny tubular scaffold, typically a mesh of fine wire woven or laser cut into a cylindrical shape. Its purpose is to prop open a blood vessel that has narrowed due to disease, usually atherosclerosis, where plaque builds up on vessel walls. Before stents, this narrowing required major surgery, bypass operations where surgeons would reroute blood flow around the blockage. Stents changed everything. A collapsed stent, crimped down to a tiny diameter, can be threaded through blood vessels on the end of a catheter. When it reaches the narrowed section, a balloon inflates inside it, expanding the stent against the vessel walls. The balloon is then deflated and removed, but the stent remains, holding the vessel open. Early stents were made of stainless steel. They worked, but they had limitations. The steel had to be expanded plastically, permanently deformed, to take its final shape. The expansion had to be precise, too much or too little, and the stent wouldn't function properly. And steel stents, once expanded, were rigid, potentially uncomfortable if they needed to flex with body movement. Nitinol transformed stent technology. A Nitinol stent can be manufactured in its expanded form, its remembered shape. Then it's cooled and compressed into its martensitic phase, collapsed down to fit inside a catheter. The compressed stent is threaded through blood vessels to the treatment site. There, body heat alone causes it to transform back to austenite, expanding to its remembered diameter with gentle, consistent force against the vessel walls. This self-expanding behavior offers remarkable advantages. The expansion is automatic, requiring no balloon inflation. The force is distributed evenly around the circumference. The stent can be designed to exert just the right amount of radial force, enough to hold the vessel open, but not so much as to damage delicate tissues. And once expanded, the supraelastic nitinol remains flexible, able to bend and flex as the patient moves, reducing irritation and improving long-term comfort. The success has been extraordinary. Millions of Nitinol stents are implanted every year worldwide. They've become standard care for coronary artery disease, peripheral artery disease, carotid stenosis. They save lives daily, preventing heart attacks and strokes, restoring circulation to endangered limbs. Guide wires tell a similar story of transformation. Before Nitinol, guide wires were made from stainless steel. They had to be stiff enough to push through blood vessels and navigate to target sites, yet flexible enough not to puncture vessel walls. This was a difficult compromise. Stiff wires pushed well, but couldn't navigate tight curves. Flexible wires navigated curves, but buckled when pushed. Nitinol's supraelasticity solved this dilemma. A Nitinol guide wire can be pushed with considerable force, yet it bends smoothly around curves without kinking or taking permanent sets. When it encounters resistance, it flexes rather than buckling or piercing. The wire can navigate the most tortuous anatomy, the twisting, turning pathways through the brain's blood vessels, the sharp angles in coronary arteries, the complex branching in peripheral vasculature. Interventional radiologists and cardiologists now routinely thread Nitinol guide wires to treatment sites that would have been unreachable with older technology. Aneurysms deep in the brain can be reached and treated. Blockages in tiny coronary branches can be opened. Complex procedures that once required open surgery are now performed through millimeter-sized incisions, with patients often going home the same day. But the mouth is another frontier where Nitinol quietly revolutionized treatment. Orthodontic wires deliver constant corrective force. Traditional orthodontic treatment used stainless steel wires to move teeth. The orthodontist would bend the wire to create forces on the teeth, gradually shifting them toward proper alignment. But steel wires delivered diminishing force as teeth moved. Every few weeks, the patient returned for adjustments, tightening the wire to restore the corrective force. This was uncomfortable. Each adjustment meant a period of significant force and discomfort as the tight wire pushed hard against teeth. As teeth moved and the wire relaxed, the force decreased and tooth movement slowed. The treatment was a series of starts and stops, uncomfortable peaks followed by periods of reduced effectiveness. Enter Nitinol arch wires. These wires are manufactured in the shape of a properly aligned dental arch, the curve that teeth should follow. At room temperature, the wire is flexible enough to be bent and tied to brackets on the patient's misaligned teeth. Once in the mouth, body heat activates the shape memory. The wire tries to return to its remembered arch form, but the teeth hold it in a distorted shape. The beauty is in the supraelasticity. As teeth gradually move toward alignment, the Nitinol wire maintains nearly constant force. It doesn't relax the way steel does. The force remains steady over the weeks and months of treatment, providing continuous gentle pressure that efficiently moves teeth without the peaks of discomfort that steel wires created. Patients experience more comfortable treatment. Fewer adjustment appointments are needed. Treatment often proceeds faster because the force remains optimal throughout. Nitinol arch wires have become standard in modern orthodontics, a quiet revolution that millions of people wearing braces benefit from without ever knowing the material science behind their treatment. But using any material inside the human body raises critical questions of compatibility. Will the body tolerate it? Will it corrode or degrade? Will it cause inflammation or immune reactions? For Nitinol, the answer lies in its surface. Titanium oxide layers improve biocompatibility. When Nitinol is exposed to air or water, the titanium at the surface rapidly forms a thin, stable oxide layer, essentially a microscopic coating of titanium dioxide, the same compound found in white paint and sunscreen. This oxide layer is biologically inert. It doesn't react with proteins or cells. It doesn't trigger immune responses. It's chemically stable, not dissolving or corroding in bodily fluids. The nickel, which could be problematic if free in the body, remains locked beneath this protective oxide shield. With proper passivation treatments to ensure a complete, uniform oxide layer, Nitinol achieves excellent biocompatibility. Years of clinical experience have validated this. Nitinol devices can remain in the body for decades without causing adverse reactions. The body's tissues grow around stents and implants without excessive inflammation. Patients with nickel allergies can often tolerate Nitinol implants safely, though extra testing and precautions may be warranted. This biocompatibility opened yet another application. SMAs are used in bone fixation devices. When bones are broken, they must be held in proper alignment while they heal. Traditionally, this meant metal plates and screws, pins, or external fixators. These devices worked, but they had drawbacks. Steel plates were stiff, stress shielding the bone, and potentially leading to weakness. Screws could loosen. Everything was permanent, requiring a second surgery for removal once healing was complete. Nitinol bone fixation devices offer advantages. Staples made of Nitinol can be cooled, expanded, and placed across a fracture. As they warm to body temperature, they contract, compressing the fracture site with consistent force and promoting healing. Plates made from porous Nitinol can flex with the bone, reducing stress shielding. Some designs are supraelastic, able to accommodate the small movements and loads that bones experience during healing without loosening or failing. Even more remarkable, porous niti matches bone stiffness. One persistent problem with metal implants is the stiffness mismatch between metal and bone. Steel and titanium alloys are much stiffer than bone. When you attach a very stiff plate to bone, the plate carries most of the load, and the bone is shielded from the stresses it needs to remain healthy. This stress shielding can lead to bone atrophy, weakening it over time. Researchers discovered that by creating porous nitinol, material with carefully controlled void spaces distributed throughout, they could tune its stiffness to match bone. The porosity reduces the overall stiffness while maintaining reasonable strength. And these porous structures offer another benefit. Bone can grow into the pores, integrating with the implant in ways that solid metal never could. These porous nitinol implants are still experimental in many applications, but they show remarkable promise. Imagine a hip implant that flexes like natural bone, that allows bone to grow into its structure, creating a strong biological bond. Imagine spinal fusion devices that support loads while allowing controlled motion, promoting fusion while preventing the excessive stiffness that can damage adjacent vertebrae. This is the frontier of orthopedic biomaterials, and nitinol is leading the way. But let us leave the human body now and venture outward to the realm beyond Earth's atmosphere. SMAs deploy satellite mechanisms. Satellites are marvels of engineering, but they face a unique challenge. They must fit inside rocket fairings for launch, then unfold and deploy once in orbit. Solar panels must extend. Antennas must unfurl. Instruments must pivot to face their targets. All of this must happen reliably in the vacuum and temperature extremes of space, often with no possibility of repair if something fails. Traditional deployment mechanisms used motors, springs, explosive bolts, and complex linkages. These worked, but they added mass, complexity, and points of failure. Every motor needs power. Every spring needs careful design to deliver the right force. Every explosive device is a single-use system that cannot be tested in its final configuration. Shape memory alloy actuators offer elegant alternatives. A simple wire or strip of SMA, properly designed and placed, can deploy a solar panel when heated. Heating can come from electrical current or simply from exposure to sunlight after leaving Earth's shadow. The deployment force is predictable, based on well-understood phase transformation behavior. The actuator can be tested repeatedly on the ground under thermal cycling, validating its performance. And once deployed, the SMA simply remains in place, adding negligible mass and no complexity. Multiple satellites have flown with SMA deployment actuators. Release mechanisms, hinge actuators, latch deployments, shape memory alloys have proven reliable in the harsh space environment. They survive launch vibrations, tolerate extreme temperature swings, and function predictably when called upon. Even more impressively, Mars rovers use SMA actuators. The Sojourner, Spirit, Opportunity, and Curiosity rovers all carried nitinol components. Some used SMA actuators to deploy wheels or position sensors. These devices had to work after months of space travel, after the violent deceleration of atmospheric entry, after the shocks of landing. And work they did every time. The Mars environment is particularly challenging. Temperatures swing from well below freezing at night to above freezing during the day. The thin atmosphere provides almost no convective cooling. Dust infiltrates everything. Yet nitinol actuators have performed flawlessly, deploying mechanisms after years of dormancy, operating in an environment no human has ever visited. Closer to home, but no less impressive, aircraft use SMAs for morphing structures. The dream of morphing aircraft, planes that can change their wing shape to optimize performance for different flight conditions, has existed since the earliest days of aviation. Birds do this naturally, changing wing configuration for takeoff, cruising, and landing. But engineering controllable wing shape changes has proven extraordinarily difficult. Traditional control surfaces, flaps, slats, ailerons, work through discrete hinged surfaces. They're effective, but not ideal. They create discontinuities in the wing surface, generating drag. They require complex mechanical systems with many moving parts. And they're limited in the types of shape changes they can create. Shape memory alloys offer a path toward true morphing. Embedded SMA actuators can bend, twist, or deform wing sections smoothly, without discrete hinges. The surface remains continuous, reducing drag. The actuation is distributed, allowing more complex shape changes. Multiple SMA elements can work together, creating compound curves and sophisticated aerodynamic profiles. Several experimental aircraft have demonstrated SMA morphing technology, wing trailing edges that curve smoothly rather than hinging sharply, winglets that change their angle to optimize for different speeds, inlet geometries that adapt to engine requirements. These demonstrations have proven the concept, though widespread adoption awaits further development of control systems, reliability validation, and certification processes. But one SMA aircraft application has already seen widespread commercial use. Jet engine chevrons reduce noise with SMAs. Chevrons are the sawtooth patterns you might notice on the trailing edge of some jet engine nacelles. These serrations help mix the hot exhaust flow with cooler ambient air, reducing the intensity of turbulent mixing noise, the roar that jet engines produce during takeoff and landing. Fixed chevrons work, but they impose a drag penalty during cruise flight when noise reduction isn't needed. What if the chevrons could deploy for takeoff and landing, then retract during cruise? This is exactly what shape memory alloy chevrons do. Made from Nitinol strips, they lie flat against the nacelle during cruise. But when activated, heated by electrical current or by routing hot bleed air, they bend into their chevron shape, providing noise reduction when and where it's needed. Boeing's 787 Dreamliner and some versions of the 737 MAX have used or tested SMA chevrons. The noise reduction helps airports meet increasingly strict noise regulations. Communities near airports experience less disturbance. And the retractability means minimal drag penalty during cruise, preserving fuel efficiency. This application represents a milestone: shape memory alloys in high-volume commercial aviation, a mature, safety-critical industry. It demonstrates the technology's reliability and cost-effectiveness for demanding applications. Indeed, aviation was one of the first fields to embrace SMAs commercially. Early aircraft used SMA hydraulic couplings. These were pipe fittings that could join hydraulic lines quickly and reliably. Manufactured in their expanded, coupled configuration, they were cooled and contracted to slide onto pipe ends. Once in place, heating caused them to expand, gripping the pipes tightly and forming a secure, leak-proof connection. These couplings were faster to install than threaded fittings, more reliable than mechanical clamps, and could be disassembled and reused with another thermal cycle. They found use in military aircraft particularly, where rapid maintenance and high reliability were paramount. While they've largely been superseded by other technologies now, they represented an important early commercial success for shape memory alloys. As you settle into rest tonight, consider the arc we've traced. From the microscopic oxide layers on a medical stent inside a beating heart, to the gossamer solar panels unfolding in the silence of space. From the gentle pressure on teeth gradually achieving alignment, to the powerful deployment of satellite mechanisms. From the bone implants supporting healing fractures, to the morphing wings dreaming of ever more efficient flight. Shape memory alloys work in all these places, quietly performing their transformations, remembering their purposes, responding to heat with reliable, predictable motion. They work in environments we can visit and environments we never will, in temperatures from freezing Mars nights to the heat of jet exhausts, in the wet chemistry of human bodies and the cold vacuum of orbital space. Each application represents years of development, rigorous testing, careful engineering. Each represents someone recognizing that a particular challenge might be met by a material that transforms and remembers. Each is a small triumph of matching material properties to application requirements. Rest well tonight, perhaps with a Nitinol device working somewhere nearby. In someone's chest maintaining blood flow, in someone's mouth guiding teeth, in a satellite passing overhead deploying its instruments, in an aircraft reducing its noise as it approaches landing. These materials serve us in countless ways, mostly invisible, almost always reliable, the fruits of decades of materials science finally ripening into practical benefit. Sleep peacefully, and let yourself transform as the alloys do, from the active waking state to the restful sleep state. a phase change as natural and necessary as martensite becoming austenite, guided by the temperature of consciousness lowering into dreams. Welcome back to this peaceful exploration of smart materials. We turn now from materials that move and transform to materials that mend and restore. Tonight, we leave behind the world of shape memory alloys and enter the realm of self-healing concrete. Where shape memory alloys respond with motion, self-healing concrete responds with repair. Both are smart, both are adaptive, but their intelligence manifests in profoundly different ways. Let your mind settle into this new landscape, where cracks close and damaged materials find wholeness again. Concrete is everywhere around us. It forms the foundations of our buildings, the spans of our bridges, the surfaces of our roads. It's the most widely used construction material on Earth, second only to water as the most consumed substance by mass. We produce more than 10 billion tons of concrete every year. It's so common, so ubiquitous, that we rarely think about it. It's just there, solid and dependable, holding up our built environment. But concrete has a fundamental weakness, an inevitable flaw built into its very nature. Concrete cracks naturally over time. This isn't a failure of engineering or manufacturing. It's not poor workmanship or inadequate design. It's simply physics and chemistry asserting themselves. Concrete will crack. The only questions are when and where. Why is this inevitable? Several reasons combine. First, concrete shrinks as it cures. When concrete is freshly mixed, it's a wet paste of cement, water, and aggregates. As the cement reacts with water in a process called hydration, the mixture hardens and gains strength. But during this process, the concrete contracts slightly. This shrinkage creates internal stresses. If the concrete is restrained, held in place by reinforcing steel, attached to existing structures, or simply resting on a friction-producing substrate, these stresses can exceed the concrete's tensile strength. Cracks form. Second, concrete is strong in compression, but weak in tension. It can support enormous compressive loads, which is why we use it for columns and foundations. But pull on concrete, subject it to tensile stress, and it fails at relatively low forces. Every structure experiences some tension, from bending, from temperature changes, from settlement. Where tension exceeds strength, cracks appear. Third, temperature changes create stress. Concrete expands when heated and contracts when cooled. On a hot summer day, a concrete bridge deck might be several centimeters longer than on a cold winter night. If this expansion and contraction is resisted or uneven, stresses develop. Again, where stress exceeds strength, cracking occurs. Fourth, loads create stress concentrations. Every time a truck crosses a bridge, every footstep on a floor, every wind gust against a building, these loads create stresses in concrete. Usually, the concrete is strong enough, but repeated loading causes fatigue. Microscopic flaws gradually grow. Eventually, visible cracks appear. So cracks are inevitable. But cracks are also dangerous, because cracks allow water and chemicals inside. A crack is a pathway, a breach in concrete's protective barrier. Water seeps in. When it freezes, it expands, widening the crack. Dissolved salts, from seawater, from de-icing chemicals on roads, penetrate through cracks. Carbon dioxide from the air enters, slowly carbonating the concrete and reducing its alkalinity. Most critically, water and oxygen reach the reinforcing steel bars embedded within the concrete. Concrete is alkaline, with a pH around 12 or 13. This high alkalinity creates a passive oxide layer on steel reinforcement, protecting it from corrosion. But when water, oxygen, and especially chloride ions reach the steel, corrosion begins. Steel corrosion is insidious. The rust that forms occupies more volume than the original steel. This expansion creates pressure against the surrounding concrete, causing more cracking. The cracks allow more water in, accelerating corrosion, which creates more expansion, which creates more cracking. It's a vicious cycle, a positive feedback loop of deterioration. As steel corrodes, it also loses cross-sectional area, weakening its load-bearing capacity. The bond between steel and concrete degrades. The the structure's strength decreases. What began as a hairline crack becomes structural distress, safety concerns, and eventually failure if left unchecked. This is why self-healing concrete repairs cracks automatically is such a revolutionary concept. Imagine concrete that could sense a crack forming and respond by filling it, sealing it, restoring the barrier. The water can't penetrate. The salts can't reach the steel. The crack doesn't propagate. The corrosion cycle never begins. The structure maintains its integrity. This isn't fantasy. It's chemistry. It's microbiology. It's materials engineering at its most creative. Researchers have developed multiple approaches to create concrete that truly heals itself. And some of these approaches are already being used in real structures. The benefits are profound. Healing extends structural service life. A typical concrete structure might be designed for a service life of 50 to 75 years. But corrosion damage often begins much sooner. Minor cracks appear within the first decade. Water penetration begins. Corrosion initiates. By 30 or 40 years, significant deterioration may be evident. Repairs become necessary. Eventually, the structure may need to be replaced or extensively rehabilitated. Now imagine concrete that heals its minor cracks before water can penetrate significantly. The corrosion timeline is dramatically extended. Instead of deterioration beginning in 10 years, it might not start for 30 or 40. Instead of major repairs at 40 years, the structure might remain sound for 70 or 80. The service life doesn't just increase incrementally, it can potentially double or more. The economic implications are staggering. If we could double the service life of concrete infrastructure, we'd effectively cut the lifetime cost in half. We'd need to build less, repair less, replace less. Resources could be allocated to new infrastructure instead of maintaining old. The environmental benefits would be equally significant. Less cement production, less demolition waste, lower carbon emissions. But how exactly does concrete heal itself? There are two fundamental approaches, and understanding the distinction between them is important. Autogenous healing uses natural cement reactions. The word autogenous means self-generated, arising from within. This type of healing relies on processes that occur naturally in concrete, without any special additives or embedded systems. Concrete contains unhydrated cement particles, cement that didn't react with water during the initial curing. When a crack forms and water enters, these particles can hydrate, forming new cement gel that deposits in the crack. Additionally, calcium hydroxide in the concrete can dissolve in the crack water and react with carbon dioxide to form calcium carbonate, a mineral that precipitates in the crack, gradually filling it. This autogenous healing has been observed in concrete for over a century. Engineers noticed that fine cracks in concrete structures sometimes seem to close over time, especially in wet environments. The phenomenon was documented, but not well understood or controlled. It was seen as a curiosity, not a design strategy. Modern research has revealed the mechanisms and conditions under which autogenous healing occurs. It works best in narrow cracks, typically less than 0.2 millimeters wide. It requires water, either because the crack is submerged or because water repeatedly enters during rain or wet conditions. It's slow, taking weeks or months for significant healing. And it's limited in extent. Cracks wider than about 0.3 millimeters rarely heal completely through autogenous processes alone. Still, autogenous healing is valuable. It's free. It happens automatically without any special materials or systems. It's passive, no trigger or activation is needed. And it's renewable, as long as unhydrated cement remains and water is available. Healing can occur repeatedly. Some researchers work to enhance autogenous healing by optimizing concrete mix designs, using supplementary cementing materials that leave reactive compounds available for later healing, or engineering the concrete microstructure to promote healing reactions. But for more reliable, more extensive healing, a different approach is needed. Autonomous healing uses added systems. Autonomous here means self-governing, able to act independently. Autonomous healing incorporates special healing agents, delivery systems, or additives into the concrete that enable more robust self-repair. These autonomous systems take many forms. Some use micro-capsules filled with healing agents dispersed throughout the concrete. When a crack breaks open capsules, the healing agent is released directly into the crack where it reacts and forms a seal. Others use hollow glass tubes or fibers filled with healing agents, achieving the same capsule-breaking release mechanism, but in a different geometry. Some systems use bacteria, living microorganisms embedded in the concrete along with nutrients. When cracks form and water enters, the bacteria activate and produce limestone, filling the crack with a mineral identical to natural calcium carbonate. Other systems use mineral-producing chemical admixtures, water-reactive swelling agents, or shape memory polymers that expand when exposed to moisture. Each autonomous system has its advantages and challenges. Encapsulation-based systems are elegant, but require that capsules survive mixing and placing without breaking prematurely. Bacteria-based systems are fascinating, but must ensure the organisms survive the harsh alkaline environment of fresh concrete and remain dormant for years or decades until needed. Chemical admixtures must not interfere with concrete's initial strength development while remaining available for healing later. Despite these challenges, several autonomous healing systems have progressed from laboratory curiosities to commercial products. Buildings have been constructed with bacteria-based self-healing concrete. Roadways have been paved with capsule-based systems. The technology is transitioning from research to reality. Across both autogenous and autonomous approaches, one factor remains critical. Healing is often triggered by water. Water serves multiple roles. It carries dissolved compounds to the crack. It enables chemical reactions, cement hydration, mineralization, bacterial metabolism. It can cause swelling agents to expand or trigger the polymerization of certain healing resins. This water-triggered healing makes sense for concrete. Concrete structures typically need self-healing most in wet environments. Marine structures, bridges exposed to rain and de-icing salts, foundations in groundwater. These are precisely the environments where water is available to trigger healing. The match between need and activation mechanism is fortunate. However, this water dependence also creates limitations. In dry climates or indoor applications with low humidity, healing may be slower or incomplete. Some healing systems require not just water presence, but repeated wetting and drying cycles to transport dissolved minerals into cracks and precipitate them. The environment influences healing success significantly. So does the damage itself. Crack size strongly affects healing success. This is perhaps the most important practical consideration for self-healing concrete. Narrow cracks heal much more readily than wide cracks. The relationship isn't linear, it's more like a threshold effect. Below certain crack widths, healing can be complete and reliable. Above that width, healing becomes partial or fails entirely. For autogenous healing, the threshold is quite narrow, typically 0.2 to 0.3 millimeters. Cracks wider than this rarely heal completely through natural cement reactions alone. There's simply too much volume to fill, and the available healing minerals are insufficient. Autonomous healing systems can often handle wider cracks, but there are still limits. A micro-capsule system might heal cracks up to 0.5 or even 1 millimeter wide if enough capsules break and release sufficient healing agent. A bacterial system might handle similar widths if enough bacteria activate and produce enough limestone. But cracks several millimeters wide generally exceed the capacity of any current self-healing system. This crack width limitation is critical for design. Self-healing concrete isn't a license to ignore crack control. Structures must still be designed and reinforced to limit crack widths. The self-healing capability is a safety net, a way to address the fine cracks that inevitably form despite good design. It's not a substitute for proper engineering. Engineers must understand this. Self-healing focuses on restoring performance rather than just appearance. This is a subtle but important distinction. When we talk about healing, what exactly do we mean? Do we mean the crack visually closes, that you can't see it anymore? Or do we mean the concrete's properties are restored? Its impermeability, its strength, its ability to protect reinforcement? It turns out visual crack closure is not always enough. A crack might be filled with healing minerals and appear closed to the eye, but if the healing material is porous or poorly bonded to the original concrete, water might still penetrate. The crack looks healed, but doesn't function as healed. Conversely, sometimes a crack that still appears slightly open may actually be well sealed. Healing minerals might bridge the crack internally, forming a barrier to water flow, even though the surface opening hasn't completely closed. The crack looks only partially healed, but functions as if fully healed. This is why researchers carefully distinguish between different measures of healing. There's mechanical healing, recovery of strength or stiffness. There's permeability healing, recovery of resistance to water flow. There's durability healing, recovery of ability to protect reinforcement from corrosion. These don't always correlate perfectly with visual crack closure. For most applications, permeability healing is most important. The primary function of self-healing is to restore the concrete's barrier properties, to stop water and aggressive chemicals from penetrating to the reinforcement. If a healing system can restore low permeability, even if the crack remains faintly visible, that's a success. If it closes the crack visually, but leaves permeable pathways, that's a failure regardless of appearance. As you rest tonight, shift your perspective from motion to repair, from transformation to restoration. Imagine not materials that bend and return, but materials that break and mend. See in your mind's eye a crack forming, a hairline fracture in grey concrete. Now watch as minerals slowly precipitate in that crack, crystals growing, filling the void. Or imagine bacteria awakening in the presence of water, beginning to feed, producing limestone grain by grain, molecule by molecule, until the crack is sealed. This is a different kind of intelligence than shape memory alloys display, but intelligence nonetheless. It's the intelligence of systems that carry their own repair kits, that sense damage and respond with healing, that don't just endure but actively restore themselves. It's concrete that behaves less like inert stone and more like living tissue, sealing its wounds before they become fatal. Let these images of healing settle in your thoughts. The slow precipitation of minerals, the patient work of bacteria, the gradual restoration of wholeness. There's something deeply satisfying about materials that heal themselves, something that resonates with our experience of biological healing, of cuts closing and bones knitting. Rest well, knowing that even as you sleep, concrete structures around the world are quietly healing themselves. Cracks are closing, minerals are forming, barriers are being restored. The built environment is becoming more resilient, more forgiving, more alive in its own way. Sleep peacefully, and let your own daily wear and tear heal in the restoration of rest, as natural and necessary as self-healing concrete mending its cracks. Welcome back to this tranquil journey through intelligent materials. Tonight we open the black box, peer inside the mechanisms, and discover exactly how concrete heals itself. These are intimate processes, molecular dances, chemical reactions unfolding in darkness within hairline cracks. Let your mind wander through these microscopic landscapes where minerals grow and bacteria awaken, where polymers swell and crystals form. There's a quiet beauty in these mechanisms, an elegance in how chemistry and biology conspire to restore what was broken. We begin with the simplest mechanism, the one that requires no special additives or systems, the healing that concrete has always possessed, but rarely exploited deliberately. Unreacted cement continues hydrating. When cement powder is mixed with water to make concrete, not all of it reacts immediately. The hydration reaction, the chemical process where cement minerals combine with water to form the hardened cement paste, takes time. Days, weeks, even months. In normal concrete, hydration proceeds most rapidly in the first hours and days. The concrete sets, hardens, gains strength. But the process doesn't truly stop. Even in year-old concrete, unhydrated cement particles remain, particularly in the cores of larger cement grains where water hasn't fully penetrated. These particles wait, dormant, unreacted. When a crack forms, it creates a new surface, exposing previously buried cement particles directly to water. Now, perhaps years after the concrete was first mixed, these particles encounter water and begin to hydrate. New cement gel forms at the crack face, slowly growing into the crack opening. Given enough time and sufficient water supply, this new cement gel can partially or completely fill narrow cracks. This process is slow and subtle. Hydration reactions at ambient temperature proceed gradually. You won't see dramatic changes hour by hour, but over weeks and months, the accumulation becomes significant. The crack that was open begins to show white mineral deposits along its faces. These deposits thicken, bridge across the gap, gradually choking off the crack pathway. The cement gel that forms is somewhat different from the original cement paste, often less dense and more porous, because it's forming in an open crack rather than in the packed mixture of fresh concrete. But even this looser gel provides significant sealing. Water flow through the crack decreases dramatically. The concrete's barrier function begins to recover. But cement hydration is only part of the story. Another mineral forms readily in cracks, sometimes even more abundantly than cement gel. Calcium carbonate precipitates in cracks. Concrete is rich in calcium. As cement hydrates, it produces calcium hydroxide as a byproduct, a highly alkaline compound that saturates the pore water in concrete. Some of this calcium hydroxide dissolves in water entering a crack. When that calcium-rich water is exposed to carbon dioxide from the air, a reaction occurs. Calcium hydroxide plus carbon dioxide yields calcium carbonate plus water. The calcium carbonate is much less soluble than calcium hydroxide. It precipitates out of solution as a solid mineral, the same mineral that forms limestone, marble, and seashells. In a crack, this precipitation can be remarkably effective. The dissolved calcium is transported into the crack by water flow. As carbon dioxide diffuses into the crack from the air, the precipitation reaction occurs right at the interface, forming calcium carbonate crystals that line and gradually fill the crack. The process is self-limiting in a useful way. As the crack fills, carbon dioxide access becomes more restricted, slowing but not stopping the healing. This calcium carbonate precipitation is the mechanism behind much of the autogenous healing observed in concrete structures. It's why cracks in concrete that's periodically wet, from rain, tides, or condensation, tend to show white mineral deposits over time. It's why some cracks in aging structures gradually become sealed, even without human intervention. But researchers wondered, could we enhance this natural process? Could we add minerals to concrete that would accelerate or expand healing capability? The answer is yes. Mineral additives enhance long-term healing. Various supplementary cementing materials and chemical admixtures can be included in the concrete mix to promote healing. Some additives provide additional sources of calcium or other reactive compounds. For example, certain types of ground limestone or calcium sulfoaluminate can react in cracks when exposed to water, forming healing minerals. Other additives modify the pore solution chemistry to favor mineral precipitation. Still others are designed to remain dormant in uncracked concrete, but react rapidly when a crack exposes them to water and air. Expansive minerals are particularly interesting. These compounds react with water to form products that occupy more volume than the original material. When incorporated in concrete and then exposed in a crack, they swell, generating pressure that physically closes the crack while also forming a mineral seal. The healing is both chemical, new minerals forming, and mechanical, expansion forcing the crack closed. The art is in selecting additives that don't interfere with concrete's initial properties. The material must still be workable when fresh, must still set at the right rate, must still achieve adequate strength. The healing additives must essentially hide in the mix, waiting for their moment to act. This requires careful formulation and extensive testing, but success stories are accumulating. Commercial mineral-based healing additives are now available and being used in real projects. Yet perhaps the most fascinating healing mechanism doesn't rely on chemistry alone, but on biology. Bacteria produce calcium carbonate. Certain species of bacteria, particularly alkalophilic bacillus strains that thrive in high pH environments, can produce calcium carbonate as a byproduct of their metabolism. When these bacteria feed on organic nutrients, they release carbonate ions that combine with calcium in the concrete to form limestone crystals. The concept is remarkable in its elegance. Bacteria are embedded in the concrete during mixing, along with a nutrient source, often something like calcium lactate or yeast extract. The bacteria remain dormant in the harsh environment of fresh concrete. But bacterial spores stay dormant until cracks form. The bacteria don't die, they sporulate, forming hardy spores that can survive for decades in the alkaline, dry, nutrient-poor environment inside concrete. When a crack forms and water enters, everything changes. The spores sense the moisture and nutrient availability. They germinate, transforming from inert spores back into active bacteria. The bacteria begin feeding on the embedded nutrients, multiplying, metabolizing, and as they do so, producing calcium carbonate. This limestone precipitates right in the crack, gradually filling it. The bacterial healing can be remarkably effective. Studies have shown healing of cracks up to 0.8 millimeters wide, much wider than typical autogenous healing can address. The bacteria work as living factories, converting nutrients into crack-filling minerals precisely where needed. Once the crack is sealed or the nutrients are exhausted, the bacteria sporulate again, returning to dormancy, ready for the next crack. This biological healing represents a profound shift in how we think about construction materials. We're no longer just mixing inert minerals and letting them harden. We're embedding living organisms, creating materials that are in some sense alive, or at least contain the dormant potential for life. It's a fusion of civil engineering and biotechnology, of construction and microbiology. The challenges are significant, of course. The bacteria must survive the mixing process, where intense shearing and heat can be generated. They must tolerate the high pH of concrete, around 12 to 13, which is hostile to most life. The nutrients must be protected, so they're available later, but don't leach out or degrade over the years. The cost is currently higher than conventional concrete, though it's decreasing as the technology matures. But the potential is extraordinary. Buildings in the Netherlands have been constructed with bacterial self-healing concrete. Parking structures, where de-icing salt exposure is severe, have used the technology. The bacteria sit dormant for years, then activate when cracks form, repairing the damage before it becomes serious. It's infrastructure that maintains itself, at least partially, using microscopic living workers we'll never see. Let's turn now to a completely different approach, one that uses synthetic rather than biological healing agents. Polymer or epoxy capsules rupturing cracks. Imagine tiny spheres, typically tens to hundreds of micrometers in diameter, barely visible to the naked eye, scattered throughout concrete. Each sphere has a thin shell, like a microscopic egg, and inside is a liquid healing agent, perhaps a two-part epoxy resin, or a cyanoacrylate adhesive, or a polyurethane precursor. These capsules are designed to be fragile enough to break when a crack propagates through them, but strong enough to survive the concrete mixing and placing process. It's a delicate balance, requiring careful engineering of the capsule wall thickness, material, and diameter. When successful, the capsules disperse uniformly through the concrete and wait, intact and ready. When a crack forms and propagates, it encounters and breaks open capsules along its path. The healing agent inside is released directly into the crack. If it's a single component system, the healing agent might cure when exposed to air or moisture. If it's a two-component system, the two parts might be in separate capsules, both breaking in the same crack and mixing together to initiate curing. As the healing agent cures, it forms a polymer seal across the crack. This seal is different from mineral healing. It's not crystalline limestone or cement gel, but a flexible, adhesive polymer. This can actually be advantageous. The polymer can bond to both crack faces, providing tensile strength across the crack. It's typically more flexible than the concrete, able to accommodate small movements without recracking. And it forms relatively quickly, hours to days rather than weeks to months for mineral healing. The encapsulation approach was inspired by biological healing. Our skin doesn't wait for minerals to precipitate when we're cut. It deploys blood platelets and clotting factors that were stored in circulation, ready for immediate deployment. Encapsulated healing agents in concrete work similarly, stored throughout the material, released on demand when damage occurs. Challenges include the cost of producing and incorporating capsules, ensuring they don't significantly weaken the concrete, and guaranteeing that enough capsules break in any given crack to release sufficient healing agent. But the approach has been demonstrated successfully in laboratory studies and small-scale field applications. Some researchers use glass tubes instead of polymer capsules, achieving similar release mechanisms with different advantages in terms of strength and compatibility with concrete. A related but distinct approach takes inspiration from biology again, but from vascular systems rather than cellular storage. Vascular systems transport healing agents. In our bodies, blood vessels form a network that can deliver healing components to any injury site. Researchers have created analogous networks in concrete, channels or tubes embedded in the material through which healing agents can flow. These vascular systems typically use hollow tubes or channels formed during casting. The channels might be created by embedding sacrificial materials that are later removed, or by using hollow tubes that remain in the concrete. The channels are filled with healing agent and sealed. When a crack intersects a channel, the healing agent is released into the crack. The advantage over capsules is volume. A capsule can only release what it contains, a tiny droplet, but a vascular channel can be connected to a reservoir, providing essentially unlimited healing agent. Large cracks or multiple cracks can be healed without exhausting the system. Some sophisticated designs use two separate vascular networks, carrying the two parts of a two-component healing agent, ensuring they only mix where cracks bring them together. The challenges include the complexity of creating and filling the channels, the potential for channels to become pathways for water ingress if damaged, and the need for reservoirs that must either be refilled manually or be large enough to serve the structure's lifetime. But for critical structures or repair applications, vascular healing shows significant promise. Now consider a mechanism that doesn't fill cracks but blocks them through expansion. Superabsorbent polymers swell to block water. These are the same materials used in disposable diapers. Polymers that can absorb many times their weight in water, swelling dramatically as they do so. When incorporated into concrete as small particles and then exposed in a crack, they absorb water and expand, physically plugging the crack. The beauty of this approach is its responsiveness. The polymer swells specifically when and where water is present, exactly where waterproofing is needed. The swelling can be rapid, occurring within minutes to hours of water exposure. And the swollen polymer creates a gel-like seal that's highly effective at blocking further water flow, even if it doesn't completely fill the crack. These superabsorbent polymers work best for waterproofing applications, basement walls, water tanks, tunnels. The goal isn't to restore structural strength, but to restore impermeability. For these applications, they're remarkably effective and relatively inexpensive. The polymers can be mixed directly into the concrete or applied as coatings or sealants. Limitations include durability questions. The swollen polymers can dry out if water access is removed, shrinking again and potentially reopening the crack. They also don't bond strongly to concrete, so while they block water flow, they don't heal cracks in a mechanical sense. But for their intended purpose of water sealing, they perform admirably. Another approach works at the crystalline level. Crystalline admixtures grow in soluble crystals. These are chemical admixtures that remain dissolved in concrete's pore water. When a crack forms and water begins flowing through it, the admixture components react with cement minerals and other compounds in the crack to form insoluble crystalline products. These crystals grow preferentially in the voids and cracks where water is flowing, gradually blocking the pathways. The mechanism is similar to how stalactites and stalagmites form in caves. dissolved minerals precipitating out where conditions favor crystal growth. The crystals essentially clog the crack from within, reducing permeability, even if they don't completely fill the crack visually. Crystalline admixtures have been used in concrete for decades, primarily for waterproofing. Their self-healing capability has been recognized more recently. They're particularly effective because they can work repeatedly. If a crack reopens or new cracks form, as long as the admixture remains available in the poor water, healing can occur again. The material has a renewable healing capacity. These admixtures are also relatively inexpensive and easy to incorporate, typically just mixed into the concrete as a powder. They don't significantly affect workability or strength. For applications where water resistance is critical, they're an attractive option. Finally, perhaps the most sophisticated approach recognizes that no single mechanism is perfect for all situations. Multiple systems can be combined. A concrete mix might include mineral additives for long-term autogenous healing, bacteria for biological healing of moderate cracks, and capsules for rapid polymer sealing of larger cracks. Each system addresses different crack sizes, different exposure conditions, different timescales. This multi-system approach is more expensive and complex, but it provides redundancy and broader healing capability. If one system is exhausted or doesn't activate in particular conditions, another might still function. The systems can even work synergistically. Bacteria might partially fill a crack, then mineral precipitation completes the sealing, for example. Researchers continue to explore optimal combinations. Which systems complement each other best? How do we avoid systems interfering with each other? What's the right balance of cost and performance? These questions drive ongoing research as self-healing concrete transitions from laboratory novelty to practical construction material. As you drift towards sleep tonight, imagine these mechanisms unfolding. See cement particles, dormant for years, suddenly encountering water and beginning their slow hydration dance, molecule by molecule building new cement gel. Watch calcium carbonate crystals nucleating, growing, their geometric perfection filling a jagged crack with ordered mineral structure. Envision bacterial spores sensing moisture, germinating, transforming from dormant to active, beginning to feed and reproduce and produce limestone, living factories operating in darkness. Picture capsules rupturing, releasing their stored healing agents like tiny pharmaceutical deliveries, precisely targeted to the site of damage. See polymer particles swelling as they absorb water, expanding to many times their original size, pressing against crack faces, creating gel seals. Watch crystals growing in flowing water, gradually narrowing the channel, slowing the flow, finally stopping it completely. Each mechanism is a small wonder of chemistry or biology or material science. Each represents human ingenuity applied to an ancient problem. How to make durable materials that don't just resist damage, but actively respond to it. Together, they're transforming concrete from a passive material into an active, responsive, self-maintaining one. Rest well tonight, knowing that multiple ingenious mechanisms are at work in concrete structures around the world, each following its own path toward the same goal: restoration, repair, healing. Sleep peacefully, and let your own body's many healing mechanisms do their work as you rest, repairing the day's small damages, restoring what was depleted, preparing you for tomorrow, just as self-healing concrete prepares itself for decades more of service. Welcome back to this gentle exploration of intelligent materials. Tonight we ask the practical questions, the questions that determine whether self-healing concrete moves from laboratory curiosity to construction standard. Does it actually work in the real world? How well does it perform? How long does it last? These are the questions engineers must answer, the bridge between scientific discovery and practical implementation. Let yourself settle into comfort as we explore the evidence, the testing, the long-term reality of materials that heal themselves. In the laboratory, under controlled conditions, self-healing concrete can seem almost magical. Cracks close, water stops flowing through, strength recovers, but the real world is messier, more variable, less forgiving. Structures experience temperature swings, alternate between wet and dry, face freeze-thaw cycles, and chemical exposure. Does self-healing work under these real-world conditions? The answer is nuanced, complex, and ultimately hopeful. But it begins with understanding what factors influence healing. First and most fundamentally, healing efficiency depends on moisture. We've mentioned that water triggers many healing mechanisms, but let's examine this dependency more deeply. Water serves multiple critical roles. For autogenous healing through cement hydration, water is a reactant. It chemically combines with unhydrated cement to form new cement gel. Without water, hydration simply cannot occur. The cement particles sit dormant, unreactive, unable to contribute to healing. For calcium carbonate precipitation, water is a transport medium. It dissolves calcium hydroxide from the concrete, carries it into the crack, and provides the aqueous environment where precipitation reactions occur. Dry cracks don't precipitate minerals. They remain open, empty, unhealed. For bacterial healing, water is essential for germination and metabolism. Bacterial spores can remain dormant in dry concrete indefinitely, but they can't activate, can't feed, can't produce limestone without moisture. The bacteria are waiting for water like seeds waiting for rain. For polymer swelling mechanisms, water is the trigger. The superabsorbent polymers remain small and inactive when dry, but swell dramatically when wet. No water means no swelling, no sealing. Even for capsule-based systems, where water isn't directly part of the healing chemistry, moisture often influences the curing of released polymers. Many epoxies and polyurethanes cure through reactions with atmospheric moisture. Completely dry conditions can slow or prevent proper curing. So moisture is critical. But how much moisture? Continuous immersion, as in a water tank or submerged marine structure, provides optimal conditions. The crack remains filled with water. Healing reactions proceed continuously. Partially submerged conditions, like tidal zones where structures are alternately wet and dry, also work well. The wet periods allow healing reactions, while dry periods may actually assist some mechanisms, allowing minerals to precipitate as water evaporates, for instance. Periodic wetting, as from rain or condensation, can still enable healing, though more slowly. Each wet period advances the healing process incrementally. Over many cycles, significant healing can occur. But truly dry environments, like indoor structures in arid climates with low humidity, present challenges. Healing is dramatically slowed, or may not occur at all without special provisions. Engineers designing with self-healing concrete must consider the expected moisture exposure. Marine structures, bridges in rainy climates, foundations in groundwater. These are ideal applications. Desert structures or indoor slabs in climate-controlled buildings are less suitable unless the self-healing system is specifically designed for low moisture conditions, or unless moisture can be supplied artificially if healing is needed. Temperature also matters significantly. Moderate temperatures improve healing. Chemical reaction rates generally increase with temperature, following principles described by the Arrhenius equation. Warmer conditions mean faster cement hydration, quicker mineral precipitation, more rapid bacterial metabolism. But there are limits in both directions. Very cold temperatures slow healing dramatically. Below freezing, liquid water becomes ice, halting most healing mechanisms. Bacteria become dormant or die. Chemical reactions slow to negligible rates. Even above freezing, cold temperatures, say 5 to 10 degrees Celsius, result in much slower healing than would occur at 20 or 25 degrees. But very hot temperatures also create problems. Above about 40 degrees Celsius, some bacterial species struggle. Above 60 degrees, many bacteria die. Polymer-based healing agents might cure too rapidly, becoming brittle or not flowing properly into cracks. The poor water in concrete can evaporate quickly at high temperatures, removing the water needed for healing. The optimal temperature range for most healing mechanisms is roughly 10 to 35 degrees Celsius. Moderate temperatures that span typical outdoor conditions in temperate climates. Fortunately, This is also the temperature range where concrete structures spend most of their service lives. Extreme temperatures, whether cold winters or hot summers, are typically temporary. Healing may pause during these extremes, but resumes when moderate conditions return. This temperature sensitivity has implications for accelerated testing. Researchers often want to observe healing quickly, not wait months or years. One approach is to use elevated temperatures to speed healing reactions. But care must be taken. Too high, and you're testing mechanisms that won't occur in real structures. The test must remain representative, even while being accelerated. Now let's turn to the fundamental challenge of testing self-healing concrete. Creating reproducible damage. Crack widths are controlled in testing. In real structures, cracks form naturally from loads, shrinkage, temperature changes, and they vary widely in width, depth, and character. For scientific study and quality control, we need to create controlled cracks of known width. Researchers use various methods. Some apply carefully controlled loads to beam or cylinder specimens until they crack. The load is precisely measured, and the resulting crack width is monitored with microscopes or digital image correlation. Others use wedges or spacers to force cracks open to specific widths. Still others create cracks through imposed deformations, bending specimens to create tensile cracks of controlled dimensions. The crack width used in testing is critical because healing capability varies dramatically with width. Most studies use cracks ranging from 0.1 mm to 0.5 mm. Narrower cracks, below 0.2 mm, often heal readily through multiple mechanisms. Wider cracks, above 0.4 mm, challenge even the best healing systems. Some researchers explore even wider cracks, up to 1 mm, to establish the limits of healing. Creating these controlled cracks isn't trivial. Concrete is heterogeneous, full of aggregates, voids, and interfaces. A crack doesn't propagate uniformly, but follows the path of least resistance, weaving around hard aggregates, sometimes branching or widening irregularly. Getting a consistent, well-defined crack of precisely 0.3 mm width is challenging. Yet without controlled crack creation, comparing different healing systems becomes nearly impossible. Once controlled cracks are created, healing is induced by exposing specimens to water or moisture under controlled conditions. Then comes measurement. What exactly are we measuring? What does healed mean quantitatively? Several metrics are used, each capturing different aspects of healing. Water permeability recovery is measured most commonly. This makes sense because water intrusion is the primary concern that self-healing addresses. Before cracking, a concrete specimen has low permeability. Water flows through slowly if at all. After cracking, permeability increases dramatically. Water flows readily through the crack pathway. After healing, the question is, has low permeability been restored? Testing involves applying water pressure to one side of a cracked specimen and measuring the flow rate through to the other side. Or it involves measuring how far water penetrates into the specimen under pressure. These tests can be repeated over time, tracking healing progress. A fully healed specimen shows permeability restored to or near pre-crack levels. Partial healing shows intermediate permeability. The results can be striking. Some self-healing concretes recover from permeability that's thousands of times higher than uncracked concrete to permeability only twice as high, nearly complete restoration. Others show more modest recovery, perhaps reducing permeability by a factor of 10 or 100. Even this partial recovery is valuable, significantly extending the time before water penetrates to reinforcement. Permeability testing is relatively straightforward and directly relevant to durability. It's become a standard method for evaluating self-healing concrete. But it's not the only important measure. Strength recovery is evaluated as well. Cracks reduce a specimen's load-bearing capacity. A cracked beam can't carry as much load as an uncracked one. After healing, does strength recover? This is tested by loading specimens to failure. First uncracked specimens to establish baseline strength, then cracked specimens to show strength loss, then healed specimens to demonstrate recovery. Strength recovery is typically less complete than permeability recovery. A crack filled with precipitated minerals or polymer isn't as strong as intact concrete. The healing material may bond imperfectly to the crack faces. The crack itself represents a plane of weakness even if filled. Studies typically show strength recovery of 30 to 80%, depending on the crack width, healing mechanism, and concrete properties. For many applications, partial strength recovery is sufficient. The structure was designed with safety factors. A crack that reduces strength by 20%, then heals to recover 15%, still leaves the structure stronger than the cracked state, and possibly within acceptable safety margins. And remember, the primary goal is usually durability protection, not strength restoration. If healing prevents corrosion, it prevents the more serious strength loss that would occur from steel deterioration. Another sophisticated measurement technique examines electrical resistivity. Electrical resistivity relates to corrosion protection. Concrete's resistance to electrical current flow correlates with its resistance to ion transport. High resistivity means low ionic conductivity, which means corrosive chloride ions move slowly. This slows the corrosion of embedded steel reinforcement. A crack dramatically lowers resistivity. It creates a high conductivity pathway. Water and dissolved ions flow easily through the crack, and electrical current follows. Measuring resistivity across a cracked specimen shows a marked decrease. After healing, if the crack is well sealed, resistivity should recover. Resistivity measurements are non-destructive, meaning the same specimen can be tested repeatedly over time without damage. This allows tracking of healing progress continuously. Some researchers use embedded electrodes in concrete specimens, monitoring resistivity in real time as healing occurs. The technique provides insight into the quality of healing. Complete sealing should restore high resistivity, while partial or porous healing may show incomplete resistivity recovery. All these tests address a single healing event, crack-heal test. But a critical question remains: can the material heal again? Some systems heal repeatedly. This is profoundly important for practical applications. A structure might experience multiple cracking events over its lifetime. Different loading conditions, earthquake aftershocks, additional settlement or temperature stresses. One-time healing is useful. Repeated healing is transformative. Autogenous healing through cement hydration and mineral precipitation can occur multiple times as long as unreacted cement remains and conditions favor precipitation. Studies have shown concrete specimens healing, being recracked, healing again, sometimes through 3 or 4 cycles. Each healing event is somewhat less effective than the previous one. Healing materials are gradually being exhausted, but the renewable capability is substantial. Bacterial healing also shows repeated capacity. As long as nutrients remain, bacteria can sporulate after one healing event, wait for the next crack, and activate again. Some studies have demonstrated 3 or more healing cycles with bacterial systems. The limiting factor is typically nutrient depletion rather than bacterial viability. Capsule-based systems, in contrast, are typically one-time healing. Once a capsule ruptures and releases its contents, it's exhausted. A new crack in a different location might encounter fresh capsules, but the same crack location can't heal again unless new capsules are somehow introduced. This limitation is significant, but not necessarily disqualifying. Many cracks, once healed, don't reopen in exactly the same location. Vascular systems can potentially heal repeatedly if connected to reservoirs that are refilled. This requires access and maintenance, but offers essentially unlimited healing capacity. For critical infrastructure, this active maintenance approach might be worthwhile. The timeline of healing varies widely, but can be remarkably extended. Healing can continue for years. In some studies, specimens examined months after initial crack exposure still show ongoing healing. Additional mineral formation, continued crack closure, progressive permeability reduction. The rate slows over time, but the process continues as long as conditions permit. This long-term healing is encouraging. It suggests that even if initial healing is incomplete, given enough time, further improvement may occur. A crack that's 80% sealed after 3 months might be 95% sealed after a year. For structures designed to last decades, this patient, gradual healing is perfectly acceptable. Field demonstrations have confirmed laboratory findings. Parking structures with self-healing concrete have been monitored for 5 to 10 years. Initial cracks that formed from shrinkage or early loading show progressive healing over the years. The cracks narrow, mineral deposits accumulate, water permeation decreases. The healing is slow, measured in years rather than days, but it's real and valuable. However, the real world introduces challenges that laboratory testing can't fully capture. Environmental exposure affects performance. Freeze-thaw cycles, where water in cracks freezes and expands, can disrupt healing. Ice formation can break newly formed healing minerals, requiring healing to begin again after thawing. Structures in cold climates experience these cycles repeatedly each winter. Chemical exposure also matters. Concrete in marine environments faces salt water, which affects mineral precipitation chemistry. Concrete exposed to de-icing salts experiences chloride ingress, which can interfere with some bacterial species. Acidic environments, like industrial areas with acid rain or certain wastewater treatments, can dissolve healing minerals as fast as they form. Mechanical loading affects healing as well. A crack that's constantly opening and closing under live loads may not heal effectively. The movement disrupts mineral formation and prevents bonding. Healing works best in cracks that are relatively stable, where healing materials can form and consolidate without being immediately disturbed. These environmental factors must be considered in design. Self-healing concrete isn't a universal solution that works equally well everywhere. It must be matched to the application, with healing mechanisms selected for the expected exposure conditions. Bacterial systems might be chosen for moderate climates with regular moisture. Mineral-based systems might be preferred for marine environments. Capsule systems might be specified for structures with stable cracks and infrequent wetting. The field is maturing, but challenges remain in establishing consistent evaluation methods. Standards for testing are still evolving. Unlike conventional concrete, which has decades of standardized testing protocols, compression tests, permeability tests, durability assessments, self-healing concrete is too new for fully developed standards. Various national and international organizations are working on this. RILAM, the International Union of Laboratories and Experts in Construction Materials, has technical committees developing recommended testing methods. ASTM and other standards organizations are considering self-healing concrete specifications. But consensus takes time. Different researchers use different crack widths, different healing durations, different measurement techniques. Comparing results across studies remains challenging. This lack of standardization slows commercialization. Designers and contractors want specifications they can write into contracts, performance guarantees they can rely on. Without standard tests and acceptance criteria, specifying self-healing concrete requires more technical knowledge and involves more risk than using conventional concrete. But progress continues. As more structures are built with self-healing concrete, as long-term performance data accumulates, as testing methods are refined and standardized, confidence grows. The technology is transitioning from experimental to established, from research novelty to construction option. The ultimate question, does it last, is being answered affirmatively with nuance. Self-healing concrete does work. It does restore impermeability, does reduce maintenance, does extend service life. But it's not magic. It requires appropriate design, suitable environmental conditions, realistic expectations. Narrow cracks heal better than wide ones. Multiple healing mechanisms work better than single systems. Adequate moisture and moderate temperatures are important. Used wisely, with understanding of its capabilities and limitations, self-healing concrete represents a genuine advance in construction materials. It won't eliminate all maintenance or make structures invincible, but it will make them more resilient, more forgiving, more durable. It will extend time between repairs, reduce life cycle costs, improve sustainability. These are real, valuable benefits. As you drift towards sleep tonight, consider the patience required for proper evaluation. Healing that takes months or years to complete. Testing that requires careful controls and repeated measurements. Standards that evolve through committee work and consensus building. There's nothing flashy or immediate about this process, but it's how technologies mature, how innovations become reliable. Imagine researchers monitoring specimens for years, measuring crack widths with microscopes, testing permeability month after month, documenting the slow but steady sealing. Picture engineers analyzing data from structures built 5 or 10 years ago, correlating laboratory predictions with field performance, learning what works and what doesn't. See in your minds the gradual accumulation of evidence, the building of confidence, the emergence of consensus. This is how trust is built in new technologies, not through hype or claims, but through patient testing, honest reporting, and years of validation. Self-healing concrete is walking this path now, proving itself crack by crack, year by year, structure by structure. Rest well tonight, knowing that the concrete around you, whether self-healing or conventional, was designed with care, tested thoroughly, built to standards refined over more than a century. And know that those standards continue to evolve, incorporating new materials, new capabilities, new ways of building infrastructure that serves us better and longer. Sleep peacefully, secure in the patient, methodical work of materials science advancing one test, one measurement, one structure at a time. Welcome back to this peaceful journey through intelligent materials. Tonight we venture beyond the controlled environment of the laboratory into the harsh realities of the field. We explore where self-healing concrete faces its greatest challenges and where it delivers its greatest value. From the corrosive embrace of seawater to the frozen depths of winter, from oil wells miles beneath the earth to bridges spanning busy highways, these are the proving grounds where theory meets necessity. Let your mind wander through these extreme environments as we discover where healing matters most. The ocean is both magnificent and merciless. Its beauty conceals a chemical aggression that has challenged engineers since humans first built near water. Marine environments demand chloride resistance. Seawater contains roughly 3.5% dissolved salts by weight, and much of that is sodium chloride, common salt. This chloride is the nemesis of reinforced concrete. Picture a concrete pier extending into the ocean, waves crashing against it with every tide, salt spray coating its surface during storms. The concrete itself can tolerate seawater reasonably well. It's alkaline, dense, relatively inert. But the steel reinforcement buried within is another matter entirely. Steel wants to rust. Only the high alkalinity of concrete's poor water keeps it protected, maintaining a passive oxide film on the steel surface. Chloride ions are small, mobile, and insidious. They penetrate concrete through any pathway available, through the porous cement paste, and especially through cracks. Once chloride reaches the steel in sufficient concentration, it breaks down the protective oxide layer. Corrosion begins. The rust that forms occupies more volume than the original steel, creating internal pressure. This pressure cracks the concrete further. More chloride enters. Corrosion accelerates. It's a vicious spiral that has destroyed countless marine structures prematurely. The traditional approach is to design concrete with very low permeability, dense mixes with low water-cement ratios, sometimes with supplementary cementing materials that refine the poor structure. Add thick concrete cover over the reinforcement, creating a long pathway for chloride to travel. Apply protective coatings. Use corrosion-resistant reinforcement. All these measures help, but cracks remain the weak point. A crack provides a highway for chloride, bypassing all the careful permeability control. This is where self-healing becomes transformative. Self-healing reduces chloride ingress dramatically. When a crack forms in marine concrete, self-healing mechanisms activate almost immediately. Water enters salt water, but water nonetheless, which triggers healing. Minerals precipitate. Bacteria activate if present. Capsules rupture. The crack begins to seal. Studies measuring chloride penetration through cracked concrete show remarkable results. Cracked conventional concrete might allow chloride to reach reinforcement depth within months in aggressive marine exposure. The same concrete with self-healing capability might extend that timeline to years or even decades. Some well-healed cracks show chloride ingress rates approaching those of uncracked concrete. This extension of time is crucial because it's not linear, it's geometric in its impact. Service life can increase from years to decades. Consider a marine structure designed for a 50-year service life. With conventional concrete, cracks form early, chloride reaches the steel within 10 years, corrosion initiates by year 15, significant damage appears by year 25, and expensive repairs are needed by year 30. The structure might last 50 years, but only with extensive maintenance and multiple repair interventions. Now consider the same structure with effective self-healing concrete. Cracks still form, that's inevitable, but they seal within weeks or months. Chloride ingress is reduced by a factor of 10 or more. Instead of reaching the steel in 10 years, it takes 30 or 40 years. Corrosion initiation is delayed from year 15 to year 45. The structure reaches its intended 50-year life with minimal repairs, maybe none at all beyond routine maintenance. And it might last 60 or 70 years, rather than barely making 50. This isn't theoretical. Demonstration projects in marine environments have shown these effects. A parking structure near the Dutch coast, built with bacterial self-healing concrete, has been monitored for over a decade. Cracks that formed from early shrinkage showed progressive healing. Chloride measurements at various depths confirm dramatically reduced penetration compared to control sections with conventional concrete. The structure is performing as hoped, self-maintaining, at least partially, buying decades of additional service life. The economic case is compelling. Marine concrete is expensive to build. The quality control, the materials, the protective measures. But repairing it is even more expensive. Access is difficult and dangerous. Corrosion damage often requires removing and replacing large sections. Structures might be taken out of service during repairs, causing economic disruption. If self-healing concrete costs 20 or 30% more initially, but eliminates or drastically reduces repairs, the life cycle cost savings are enormous. But the ocean isn't the only harsh environment challenging concrete. Let us travel north, to regions where winter dominates, where temperatures plunge below freezing for weeks or months. Freeze-thaw cycles cause repeated microcracking. When water in concrete's pores freezes, it expands by roughly 9%. This expansion creates internal pressure. If the concrete has adequate air voids, tiny bubbles distributed throughout, these voids provide relief space for the expanding ice. The concrete survives. But if the concrete is saturated, if its air void system is inadequate, the pressure from freezing water can exceed the concrete's tensile strength. Microscopic cracks form. They're tiny at first, barely visible, but they're damaged nonetheless. When the concrete thaws, water enters these new cracks. The next freeze cycle widens them. Over hundreds of freeze-thaw cycles, a typical winter in cold climates, the cumulative damage becomes significant. The concrete surface begins to flake and spall, a process called scaling. Deeper damage can compromise structural integrity. Roads and bridges in northern regions face this challenge intensely. They're wet from rain and snow. They're treated with de-icing salts, which actually make the freeze-thaw problem worse by keeping water liquid at lower temperatures, allowing more freeze-thaw cycles to occur. The combination of mechanical damage from freezing and chemical attack from chlorides creates particularly aggressive conditions. Traditional defenses include air entrainment, creating those protective air voids, and using low permeability concrete to resist water saturation. These measures help but don't eliminate freeze-thaw damage, especially once cracks form for other reasons. A cracked concrete surface allows water accumulation that air entrainment can't protect against. Self-healing offers hope, but faces challenges in cold climates. Specialized systems address cold climates specifically. Most healing mechanisms slow or stop at low temperatures. Cement hydration is sluggish below 10 degrees Celsius and nearly stops below freezing. Bacterial metabolism shuts down in cold. Mineral precipitation slows dramatically. But researchers have developed cold-adapted approaches. Some use bacteria species or strains selected for cold tolerance, able to remain active at temperatures near freezing. Others use chemical healing agents that remain liquid and reactive at low temperatures. Encapsulated systems can be designed with healing agents that cure even in cold, taking advantage of brief above-freezing periods to flow into cracks before temperatures drop again. Another approach is seasonal healing. During winter, when temperatures are reliably below freezing, healing is minimal. But during spring, summer, and fall, when conditions are favorable, healing proceeds. Cracks that formed over winter gradually seal during the warm months, restoring protection before the next winter arrives. This seasonal rhythm means healing is slower, taking a full year rather than weeks or months, but it still provides significant benefit over no healing at all. Field trials in Nordic countries and Canada are testing these cold climate systems. Early results are encouraging. Healing does occur, though more slowly than in temperate climates. The key is ensuring cracks remain narrow enough that even partial healing significantly reduces water access. Combined with good air entrainment and low permeability, self-healing provides an additional layer of protection that can extend the service life of concrete in these harsh conditions. Let us descend now, deep beneath the surface, to environments even more extreme than the frozen north or the corrosive sea. Oil and gas wells need crack sealing for their cement linings. When oil or gas wells are drilled, they're lined with steel casing to prevent collapse. The space between this casing and the borehole wall is filled with cement. Not quite the same as structural concrete, but similar in many ways. This cement serves critical functions. It supports the casing. It seals formations to prevent fluid migration between different geological layers, and it protects the casing from corrosive formation fluids. But this cement faces extraordinary stresses. The well might be several kilometers deep. Pressures can reach hundreds of atmospheres. Temperatures can exceed 100 degrees Celsius, or even higher in deep wells. The cement is subjected to pressure cycling as the well is drilled deeper, as production begins, as fluids are injected or extracted. Thermal cycling occurs as hot production fluids flow through the cold casing, or as steam is injected for enhanced recovery. All these stresses cause cracking. A crack in well cement is serious. It can allow oil or gas to migrate upward along the outside of the casing, potentially reaching the surface or contaminating groundwater aquifers. It can allow corrosive fluids to reach the steel casing, initiating corrosion. It can compromise well integrity and safety. Traditional well cement uses special formulations for these extreme conditions, but cracking still occurs. Self-healing cement for wells is an active research area. Some systems use expansive minerals that react with formation fluids to swell and seal cracks. Others use oil-activated healing agents that remain dormant in the presence of formation water, but react and seal when they contact oil or gas, exactly when sealing is most needed. Even more extreme are geothermal wells. Geothermal wells face high temperature and pressure in conditions that make oil and gas wells seem mild. Temperatures can reach 200 to 300 degrees Celsius, or higher in deep geothermal systems. The fluids are often highly corrosive, acidic or containing dissolved minerals that attack cement. Thermal cycling is severe as hot geothermal fluids are produced and cooler fluids are injected for reservoir management. Standard cement systems degrade rapidly in these conditions. Specialized high-temperature cements have been developed, but they still crack, and those cracks accelerate degradation. Self-healing systems for geothermal applications must themselves survive extreme conditions. Healing must survive harsh conditions to be useful. This means bacteria won't work. They can't survive 200-degree temperatures. Polymer capsules won't work. Most polymers degrade or melt at these temperatures. Instead, researchers explore mineral-based systems, special additives that remain stable at high temperatures, but react to seal cracks when exposed to formation fluids. crystalline admixtures that grow crystals even in hot, aggressive solutions. Expansive minerals stable enough to survive the heat, yet reactive enough to seal cracks. The challenge is daunting, and success is still limited. Some systems show promise in laboratory tests at elevated temperatures, but field validation is difficult and expensive. Geothermal wells are fewer and more expensive than oil wells. Instrumenting them to monitor cement healing is complex, but the need is real. If self-healing cement could significantly extend geothermal well life, it would improve the economics of geothermal energy, supporting the transition to renewable power. These extreme applications, marine structures, freeze-thaw environments, oil wells, geothermal systems, represent the frontier of self-healing concrete. But most applications are less extreme, closer to everyday construction. Large-scale field trials prove feasibility in normal conditions. Around the world, demonstration structures have been built with self-healing concrete, and they're being monitored to validate performance. A highway bridge in the Netherlands incorporates bacterial self-healing concrete in its deck. Sensors embedded in the concrete monitor crack formation and healing, temperature, and moisture. After 5 years, the data shows cracks healing as designed, with no sign of the accelerated deterioration typical in conventional bridge decks. The Netherlands has been particularly aggressive in developing and testing self-healing concrete, motivated by extensive infrastructure in marine and water-saturated environments. Parking structures in several countries use self-healing concrete. These buildings face de-icing salt exposure, freeze-thaw cycles, and constant wetting from rain and car wash water, an aggressive combination. Structures with self-healing concrete show less deterioration than comparable conventional structures after 5 to 10 years of service. The differences are still modest. We're talking about condition ratings of excellent versus good, rather than dramatic failures prevented. But the trend is clear and encouraging. Water storage tanks, tunnel linings, basement walls, applications where water resistance is critical, have been built with self-healing concrete. Some use bacterial systems, others use crystalline admixtures or encapsulated healing agents. The variety of systems being tested reflects both the immaturity of the field. We don't yet know which approach is best, and its richness. Multiple solutions exist for different requirements. But field results vary with exposure, as laboratory studies predicted. A parking structure in a mild coastal climate shows excellent healing. The same bacterial system in an inland desert climate shows minimal healing due to insufficient moisture. A crystalline admixture system performs well in a water tank, but shows little benefit in an indoor floor slab that rarely gets wet. This variability isn't a failure of the technology. It's a reminder that self-healing concrete isn't a universal solution, but a suite of tools that must be matched to applications. The engineer's task is understanding which healing mechanism suits which environment, which combination of factors will allow healing to occur reliably over the structure's lifetime. Some projects have been disappointments. A bridge deck that cracked wider than expected, exceeding the healing capacity of the system. A water tank where the bacterial nutrients leached out during the first years, leaving no healing capacity for later cracks. A tunnel where the encapsulated healing agents proved incompatible with the admixtures used for other properties, causing both to fail. These failures are valuable too. They teach us what doesn't work, what interactions to avoid, what limits to respect. The field is learning, accumulating knowledge from both successes and failures, gradually building the understanding needed to deploy self-healing concrete reliably and confidently. As you settle into rest tonight, imagine these structures scattered across the world. A bridge in the Netherlands, its bacterial concrete quietly healing cracks between sensor readings. A parking garage in Norway, its crystalline admixtures precipitating minerals in cracks through another freeze-thaw cycle. An oil well in Texas, its self-healing cement sealing a crack before gas can migrate. A marine pier in Japan, minerals filling a crack before chlorides can penetrate to its steel. Each structure is an experiment, a demonstration, a proof point. Each contributes data to our growing understanding. Some perform brilliantly, exceeding expectations. Others struggle, revealing limitations. Together, they're charting the path from laboratory promise to construction reality. Consider the patience required for this validation. Structures must be monitored for years, sometimes decades, to truly assess durability improvements. The researchers who designed a demonstration structure in 2010 are still collecting data, still publishing papers analyzing its performance. The engineers who specified self-healing concrete in 2015 are watching it carefully, hoping their confidence was justified, learning lessons for future projects. This is infrastructure development in real time, slow, methodical, evidence-based. Not the stuff of headlines or viral videos, but the steady work of building knowledge, validating technologies, and improving how we construct the built environment. It's unglamorous but essential, and it's happening right now in structures around you, around the world. Rest well tonight, knowing that materials science doesn't stand still, that concrete, ancient and seemingly unchanging, is still evolving, still improving. Sleep peacefully, secure in the knowledge that the infrastructure serving you was built with care, and that the infrastructure being built today incorporates lessons learned from decades of research, testing, and field validation. Let your mind settle like minerals precipitating in a crack, slowly, naturally, finding the right configuration, sealing what was open, restoring what was broken, making whole what was damaged. Welcome to the final chapter of this gentle journey through intelligent materials. Tonight we look forward toward a future where structures think, respond, adapt, and heal. We've explored the science of shape memory alloys and self-healing concrete, examined their mechanisms and applications, tested them against harsh realities. Now we ask, what does all this mean for the future? How will these technologies transform the built environment? Let yourself drift into this vision of tomorrow as we complete our exploration, bringing together everything we've discovered into a picture of infrastructure that's smarter, more resilient, more sustainable. The promise of self-healing concrete and shape memory alloys isn't just technical elegance or scientific fascination. It's fundamentally economic. Self-healing reduces life cycle costs in ways that reshape the entire calculation of infrastructure investment. To understand this, we must think beyond initial construction costs to the total cost of ownership over a structure's lifetime. Traditional infrastructure analysis focuses heavily on construction cost. A bridge might cost $100 million to build. That's the number that appears in budgets, that politicians debate, that determines whether projects get funded. But construction cost is only the beginning. Over the bridge's 50 or 75-year lifetime, maintenance costs accumulate. Inspection costs, repair costs, costs of traffic disruption during maintenance. Eventually, replacement costs. Studies suggest that maintenance and operating costs over a structure's lifetime can equal or exceed the initial construction cost. A $100 million bridge might consume another $100 million in maintenance and repairs over its service life. Sometimes more, especially if early deterioration requires major interventions. The true lifetime cost is the sum, initial construction plus all subsequent maintenance and repairs, adjusted for the time value of money. Self-healing concrete changes this equation. By reducing the rate of deterioration, it extends the time between required repairs. By sealing cracks before they allow corrosion, it prevents the expensive damage cascades that drive major rehabilitation projects. Initial construction cost might increase. Self-healing concrete currently costs perhaps 10 to 30% more than conventional concrete, depending on the system and application. But lifetime maintenance costs can decrease by 50% or more. The math becomes compelling. Spend 10% more initially, save 50% on maintenance, and you've reduced total lifetime cost by 20 to 30% or more. Add to that the reduced disruption costs. Fewer lane closures, less traffic congestion, fewer business interruptions near construction zones, and the economic case strengthens further. Add the environmental benefits we'll discuss shortly, and self-healing concrete begins to look not just economically rational, but economically superior for many applications. This calculation improves as the technology matures. As production scales up, as more suppliers enter the market, as application techniques are refined, the premium for self-healing concrete will likely decrease. Some researchers believe self-healing systems could eventually add only 5% to concrete costs, while still delivering substantial maintenance savings. At that point, not using self-healing concrete for critical infrastructure might be difficult to justify. The economic benefit stems largely from one key factor: maintenance and downtime decrease. Consider a highway bridge. In conventional practice, it's inspected every 2 years. Minor repairs might be needed every 5 years. Patching cracks, replacing delaminate concrete, repairing joints. Major maintenance might be required every 15 to 20 years. Deck overlay or replacement, joint rehabilitation, bearing repairs. These interventions require lane closures, sometimes full bridge closures. Traffic is disrupted. Commerce is delayed. The direct cost of repairs is only part of the economic impact. With self-healing concrete, the timeline stretches. Minor repairs that were needed every 5 years might be needed every 10 or 15 years. Major maintenance at 20 years might be delayed to 35 or 40 years. Some interventions might be avoided entirely. The bridge still requires inspection. We can't yet eliminate the need for monitoring. But what inspectors find is less urgent, less extensive, less expensive to address. Downtime particularly matters for critical infrastructure. A manufacturing plant can't produce if access roads are closed. Port operations suffer if bridge restrictions limit container truck movements. Emergency response is compromised if bridges close unexpectedly due to deterioration. The economic value of keeping infrastructure operational, of avoiding unplanned closures, of maintaining reliable access is difficult to quantify precisely, but enormously significant. Self-healing concrete contributes to this reliability. By slowing deterioration, it reduces the likelihood of emergency closures. By maintaining structural capacity longer, it postpones load restrictions that limit what vehicles can cross. By preventing sudden failures, it allows maintenance to be scheduled proactively rather than performed reactively. Infrastructure becomes more predictable, more dependable, more valuable to the society it serves. Beyond economics, there's another powerful driver: sustainability. Environmental impacts are reduced through multiple mechanisms. First, extending structure lifetime directly reduces environmental impact per year of service. A bridge that lasts 80 years rather than 50 provides 60% more service years for essentially the same environmental cost of construction. Averaged over the longer life, the environmental impact per year of service drops by nearly 40%. Second, reducing repairs means less construction activity throughout the structure's life. Each repair cycle consumes materials: concrete, steel, sealants, coatings. It consumes energy for demolition, transportation, and reconstruction. It generates waste from removed material. Fewer repairs mean less resource consumption, less energy use, less waste generation. Third, concrete production itself is carbon intensive. Cement manufacturing produces roughly 8% of global CO2 emissions. Anything that extends concrete structure lifetime or reduces concrete consumption contributes to climate change mitigation. If self-healing concrete allows the global concrete infrastructure to last 30% longer before replacement, the reduction in cumulative cement demand and associated emissions would be globally significant. But there's an even more direct environmental benefit. Industrial byproducts can enhance healing. Several self-healing mechanisms can incorporate waste materials that might otherwise be discarded. Fly ash from coal power plants can be used as a supplementary cementing material that also provides minerals for autogenous healing. Blast furnace slag from steel production can serve similar functions. Some bacterial healing systems use organic waste streams as nutrient sources for the bacteria. This transforms waste into value. Materials that would occupy landfills or require disposal instead become functional components of self-healing concrete. The environmental benefit is double. Waste is diverted from disposal, and the resulting concrete has improved long-term durability. It's an elegant example of industrial ecology, where one industry's waste becomes another's resource. Researchers continue exploring these opportunities. Can algae-based nutrients support bacterial healing while consuming CO2? Can recycled concrete fines, the dusty residue from crushing demolished concrete, serve as healing minerals? Can various industrial byproducts be processed into micro-capsules or healing agents? The answers are emerging, and they're often positive, opening paths to self-healing systems that are both effective and environmentally beneficial. The vision extends beyond just the materials to how we build. Self-healing integrates at multiple scales. At the smallest scale, it's engineered into the concrete mix, bacteria and nutrients thoroughly distributed, capsules uniformly dispersed, chemical admixtures properly proportioned. At an intermediate scale, it's designed into structural elements, vascular networks embedded in beams, healing systems concentrated in high-stress regions, redundant mechanisms for critical sections. At the largest scale, it's incorporated into whole structure design. Engineers select which elements should use self-healing concrete and which can use conventional material. They design joints and connections to limit crack widths to healable ranges. They detail reinforcement to work synergistically with healing mechanisms, perhaps using shape memory alloys that return to their original position after loading, reducing residual crack widths and improving healing effectiveness. This multi-scale integration requires new design approaches and new tools. Software is being developed to model self-healing concrete behavior, predicting healing rates under various exposure conditions, estimating long-term durability performance. Design guidelines are emerging, codifying best practices for applying self-healing technology effectively. The infrastructure is being built, not just physical infrastructure, but the intellectual and professional infrastructure of knowledge, standards, and expertise. New construction methods are incorporating healing from the start. 3D printed concrete may include healing functions. Additive manufacturing of concrete, building structures layer by layer using robotic printers, is advancing rapidly. This technology offers unprecedented control over material placement and composition. Each printed layer can have customized properties. Healing agents could be concentrated in specific layers or regions where cracking is most likely. Capsules could be oriented for optimal rupture. Vascular channels could be printed directly into the structure rather than embedded as separate elements. The marriage of 3D printing and self-healing creates possibilities impossible with conventional construction. Imagine a printed bridge pier where every layer is optimized, dense, low permeability concrete in the outer layers for maximum protection. More porous concrete with abundant healing capacity in inner layers, where cracks might propagate. Vascular networks printed throughout connected to external reservoirs for long-term healing capacity. The structure becomes a sophisticated, three-dimensional composition of materials and functions, rather than a simple monolithic mass. This future is closer than you might think. Researchers have already printed small-scale structural elements with embedded healing systems. Companies are developing printable self-healing concrete formulations. Within years, we may see demonstration structures combining both technologies. Within a decade, it could be standard practice for certain applications. But new technologies require frameworks for acceptance and use. Codes and certification are under development. Building codes specify minimum requirements for structural materials and design. For concrete, these codes have evolved over more than a century, incorporating countless lessons from research and field experience. Self-healing concrete is too new to be comprehensively covered in most codes. Some jurisdictions allow its use under alternative compliance paths or experimental provisions, but mainstream code acceptance requires more evidence, more standardization, more consensus. Multiple organizations are working toward this. Technical committees are drafting specifications for self-healing concrete, defining testing methods, establishing performance criteria. These documents will form the basis for code provisions. The process is slow, rightfully so, given that building codes ensure public safety, but progress is steady. Some codes already reference self-healing concrete in sections on durability design. More comprehensive coverage will follow as the technology matures. Certification programs are emerging too. Third-party testing laboratories are developing protocols to verify self-healing performance. Manufacturers will be able to have their products certified as meeting specific healing standards, giving designers and contractors confidence in performance. Insurance companies and warranty providers are watching closely. Reliable certification could enable performance warranties that guarantee healing effectiveness, further accelerating adoption. Now, let us bring together the two threads we've followed throughout this journey. Shape memory alloys and self-healing concrete can work together synergistically. Imagine a building designed to survive major earthquakes. The columns and beams use reinforcement made from shape memory alloy bars. The concrete itself is self-healing, with bacterial or capsule-based systems throughout. During an earthquake, the structure flexes and sways. The shape memory alloy reinforcement yields, absorbing energy, preventing catastrophic failure. Cracks form in the concrete. They're inevitable under such extreme loading. But after the shaking stops, the shape memory alloy, heated by the energy absorbed during yielding or by active heating systems, transforms and returns to its original shape. It pulls the structure back toward true, reducing permanent deformation and residual crack widths. Now the self-healing concrete activates. The narrow cracks left after the shape memory alloys have partially closed are within the healable range. Water from broken pipes or rain enters the cracks. Bacteria germinate, capsules rupture, minerals precipitate. Over days and weeks, the cracks seal. The structure has not just survived the earthquake, but has partially healed itself, restoring protective cover over reinforcement, recovering impermeability, preparing for the next potential event. This isn't fantasy. Structures may recover after earthquakes using precisely this combination. Research projects in Japan, New Zealand, and California are developing earthquake-resilient structures, combining shape memory alloys and self-healing concrete. Small-scale shake table tests have demonstrated the concept. The structure undergoes severe simulated earthquake loading, then recovers. Shape memory alloys returning to position, concrete healing its cracks. After recovery, the structure can withstand additional earthquake simulations, something conventional structures often cannot do after major damage. The vision is of seismically active cities, where major earthquakes don't destroy infrastructure, but merely damage it in ways that heal naturally over the following weeks and months. Buildings don't collapse or become unsafe. Bridges remain functional, perhaps with temporarily reduced capacity that's then restored through healing. Water tanks and pipes self-seal their earthquake-induced cracks. The city can begin recovery immediately rather than spending years on structural repairs. This is the ultimate promise of smart materials. Future infrastructure may adapt, heal, and endure in ways previous generations could barely imagine. We've spent our entire history building with inert materials: stone, wood, metal, concrete, that simply sit there, passively resisting forces, slowly accumulating damage, inevitably deteriorating. We've accepted that structures require constant maintenance, that they have finite lifetimes, that they must eventually be replaced. But what if they didn't have to be that way? What if structures could respond to their environment, adapt to conditions, repair damage automatically? What if bridges adjusted their camber in response to traffic loads using shape memory actuators? What if buildings stiffen their connections during high winds and soften them during earthquakes, optimizing response for different hazards? What if roads healed their own cracks before potholes could form, and dams sealed their own seepage paths before they became failures? This is the trajectory we're on. Self-healing concrete and shape memory alloys are just the beginning. Researchers are exploring other smart materials. Self-sensing concrete that detects its own damage through embedded sensors or changes in electrical properties, self-cleaning surfaces that break down pollutants using photocatalysis, self-insulating materials that adjust thermal properties based on temperature, phase-change materials that store and release heat to regulate temperature. The infrastructure of the future will be multifunctional, responsive, resilient. It won't just bear loads and span spaces. It will sense conditions, respond to changes, adapt to circumstances, heal damage, and optimize performance continuously. It will last not decades but centuries, not through massive overdesign, but through intelligent responsiveness. It will require less maintenance, consume fewer resources, generate less waste, and serve more reliably than anything we've built before. This future is being created now, in laboratories and on construction sites, through patient research and bold demonstration projects. Every bacterial self-healing concrete test, every shape memory alloy actuator development, every field trial and performance measurement is a step toward this smarter infrastructure. The path is long, decades of work remain, but the direction is clear, the progress is real, and the destination is worth the journey. As you drift into sleep now, at the end of our exploration, let your mind rest on this vision of tomorrow. See cities where buildings stand for centuries, maintaining themselves, healing their damages, adapting to changing conditions. Imagine bridges that survive earthquakes and slowly straighten themselves afterward, their cracks sealing over the following weeks. Picture roads that remain smooth year after year, their minor cracks healing before they grow, their concrete eternally restoring itself. This isn't a fantasy of distant futures or impossible technologies. This is the natural evolution of civil engineering, the next chapter in humanity's long story of building shelter, creating infrastructure, shaping the environment to serve our needs. We've progressed from mud and straw to fired brick, from brick to steel and concrete, and now we're progressing again, to materials that aren't just stronger or cheaper, but smarter, more capable, more alive in their own way. Consider the journey we've taken together through these quiet hours. We've explored atoms rearranging themselves between crystal phases, returning to remembered shapes when heated. We've watched bacteria awakening in cracks, producing limestone to seal their concrete homes. We've seen capsules rupturing to release healing polymers, minerals precipitating to fill voids, shape memory alloys generating force through phase transformation. We've examined applications from the intimate, inside human arteries and mouths, to the vast bridges, buildings, and oil wells. We've tested these materials against harsh realities: seawater and salt, freezing winters and scorching summers, earthquake shaking and constant traffic loading. We've measured their healing, quantified their performance, validated their benefits. And we've looked forward to a future where these technologies mature and combine, where smart materials become standard rather than exceptional, where infrastructure truly serves humanity better, lasting longer, costing less, harming the environment less, failing less catastrophically, recovering more gracefully from the inevitable damages that time and use inflict. This is the promise of materials science applied to construction. Not just buildings and bridges, but intelligent infrastructure that partners with us in creating durable, sustainable civilization. It's a grand vision built on molecular-scale phenomena, atoms bonding and rearranging, bacteria metabolizing and producing minerals, polymers curing and bonding, crystals growing and filling voids. From the smallest scale to the largest, from laboratory benchtop to global infrastructure, from today's tentative demonstrations to tomorrow's widespread deployment. This is the arc of progress in smart materials. You've been part of this journey, following this exploration through the quiet hours, learning about technologies that will shape the built environment for generations to come. Rest now, deeply and peacefully. Let these ideas settle in your mind like the final calm at the end of a long journey. Know that while you sleep, concrete is healing somewhere, shape memory alloys are transforming somewhere, researchers are testing somewhere, and the future is being built, patiently, methodically, inevitably, one innovation at a time, one structure at a time, one healed crack and recovered shape at a time. Sleep well, secure in the knowledge that human ingenuity continues its patient work, that materials grow ever more capable, that the infrastructure serving us becomes smarter and more resilient with each passing year. And when you wake, you'll move through a world built largely of conventional materials, but increasingly incorporating these smart technologies. Invisible, reliable, quietly making everything better, lasting longer, serving more faithfully. Good night. Rest deeply. And may your sleep be as peaceful as minerals slowly precipitating in darkness, as natural as phase transformations following thermodynamic laws, as restorative as self-healing concrete mending itself, ready for tomorrow.